Wherever you're tuning in from, whatever the hour, I'm grateful you're here. Comment your time and place below. It's always beautiful to see where in the world we're all gathering, to imagine another one. In this video, you'll first explore everything we know about Mars so far, from ancient Martian riverbeds to dust storms the size of continents, from robotic explorers still whispering data across millions of miles, to the frozen secrets buried just beneath its blood-red soil. But then, we'll shift. Because this isn't just about what was, it's about what could be. What would it mean to build a world here? What will Martian cities look like? Can we grow life in alien soil? The second half of this journey is a glimpse into the future, a vision of what Mars could become, shaped by science, ambition, and the unbreakable human urge to reach beyond. The visuals are here if you'd like to watch. But feel free to close your eyes, breathe, and drift through the red sands of past and future. Let's begin. Welcome to this gentle exploration of the cosmos, where we'll journey through the mysteries of the red planet Mars, that rusty beacon in our night sky that has captured human imagination for millennia. As you settle into your favorite listening spot, perhaps you'd like to share in the comments where in the world you're tuning in from tonight and what draws you to Mars. There's something wonderfully fitting about contemplating distant worlds while we're all scattered across our own spinning planet, each of us gazing up at the same stars that have guided explorers and dreamers for countless generations. If you find these quiet cosmic journeys soothing, I'd be grateful if you'd consider subscribing. So let your breathing slow, allow your mind to wander across the 140 million miles of space that separate us from Mars, and prepare to discover a world that is both utterly alien and surprisingly familiar. A world of towering volcanoes and vast canyons, of polar ice caps and ancient riverbeds, of dust storms that can engulf an entire planet, and seasons that last twice as long as our own. Mars has been humanity's most studied planetary neighbour, scrutinised through telescopes for centuries, and visited by dozens of robotic explorers over the past 50 years. Yet for all our observations and measurements, for all the data we've collected, and the images we've captured, Mars remains tantalizingly mysterious. It's a world that seems to hover just at the edge of our understanding, revealing its secrets slowly, reluctantly, like an ancient manuscript being translated one word at a time. The story of Mars begins not with the planet itself, but with its discovery in the minds of ancient civilizations who first noticed this peculiar wandering star. To the naked eye, Mars appears as a reddish point of light that moves against the backdrop of fixed stars, sometimes racing forward in its celestial path, sometimes stopping and occasionally moving backward in what astronomers call retrograde motion. This strange behavior puzzled ancient observers and earned Mars its association with chaos and war. The ancient Egyptians called it Har-Decher, meaning the Red One. The Greeks named it Ares after their god of war, while the Romans, from whom we inherit the name Mars, associated it with their own deity of warfare. But it was this seemingly erratic motion that made Mars so fascinating to early astronomers. They couldn't understand why this particular wandering star refused to follow a predictable path across the heavens like the sun and moon. The mystery of Mars's retrograde motion wouldn't be solved until the 16th and 17th centuries, when astronomers like Copernicus and Kepler revolutionized our understanding of the solar system. They realized that Mars appears to move backward, not because it actually reverses direction, but because Earth, traveling in a smaller, faster orbit, periodically overtakes Mars like a race car passing on an inner track. As Earth catches up to and passes Mars, the red planet appears to slow down, stop, and move backward against the stellar backdrop before resuming its forward motion. This elegant explanation transformed Mars from a chaotic wanderer into a predictable neighbor, following the same gravitational laws that govern all planetary motion. But even as the mechanics of Mars's orbit became understood, the planet itself remained shrouded in mystery. Early telescopic observations in the 17th and 18th centuries revealed tantalizing hints of a world that might be similar to Earth. Astronomers observed what appeared to be polar ice caps that grew and shrank with the seasons, suggesting a planet with a tilted axis and seasonal cycles much like our own. They noted that a Martian day, or sol, as it's now called, lasts about 24 hours and 37 minutes, remarkably close to Earth's 24-hour day. 5-degree tilt, giving Mars seasons that, while lasting twice as long due to Mars's longer year, follow familiar patterns of summer and winter, spring and fall. These observations led to centuries of speculation about what kind of world Mars might be. If it had ice caps and seasons, if its day was nearly the same length as Earth's, might it not also harbor life? This question would drive Mars exploration for the next 3 centuries, inspiring both rigorous scientific investigation and flights of imagination that would profoundly influence human culture. The most famous of these speculative leaps came in the late 19th century, when Italian astronomer Giovanni Schiaparelli reported observing what he called canali on Mars's surface. The Italian word canali simply means channels, but when translated into English as canals, it suggested something far more provocative: artificial waterways constructed by intelligent beings. American astronomer Percival Lowell seized upon this idea, establishing an observatory in Arizona dedicated to studying Mars and mapping what he believed to be an extensive network of irrigation canals built by a dying Martian civilization. Lowell's Mars was a world of engineering marvels, where an ancient and sophisticated society had responded to their planet's gradual desiccation by constructing a global network of waterways to transport precious water from the polar ice caps to populated regions near the equator. He wrote eloquently of these Martians, describing them as beings far more advanced than humans, who had achieved a level of planetary cooperation that Earth's quarreling nations could only dream of. In Lowell's vision, Mars was a world without borders, where the struggle for survival had united all inhabitants in common purpose. G. Wells's The War of the Worlds to Edgar Rice Burroughs's John Carter Adventures. Mars became the archetypal alien world, close enough to Earth to be reachable, different enough to be exotic, and mysterious enough to serve as a blank canvas for human hopes and fears about life beyond our planet. But as telescopic technology improved throughout the 20th century, the evidence for Lowell's canal-building Martians began to evaporate. Better observations revealed that the supposed canals were optical illusions, tricks of light and shadow that the human brain interpreted as linear features. The romantic vision of a dying civilization on Mars gradually gave way to a more sobering reality. Mars appeared to be a cold, dry, and lifeless world, more alien than anyone had imagined. The first close-up images of Mars, captured by NASA's Mariner 4 spacecraft in 1965, seem to confirm this bleak assessment. The photographs revealed a heavily cratered surface that looked more like the Moon than the Earth-like world that many had hoped to find. There were no cities, no canals, no obvious signs of life, or even the conditions that might support life. Mars appeared to be a dead world, its surface scarred by billions of years of meteorite impacts and erosion, its atmosphere too thin to support liquid water or protect against the harsh radiation of space. Yet even as these early images dashed hopes for an inhabited Mars, they revealed a world of unexpected geological complexity and beauty. The craters told a story of Mars's violent early history, when the young solar system was still filled with debris left over from planetary formation. But between the craters, scientists noticed other features that hinted at a more dynamic past. Ancient impact basins, mysterious smooth plains, and what appeared to be enormous volcanic mountains rising from the planet's surface. These tantalizing glimpses would drive the next phase of Mars exploration, as scientists realized that while Mars might not harbor the advanced civilization that Lowell had imagined, it was clearly a world with its own fascinating geological story to tell. The quest to understand Mars was just beginning, and each new discovery would reveal a planet far stranger and more complex than anyone had anticipated. As we pause in our journey through Mars's story, let your mind drift across that vast gulf of space that separates our two worlds. Imagine the red planet hanging in the cosmic darkness, its rusty surface bathed in the pale light of a sun that appears only half as bright as it does from Earth. Picture the ancient impact craters that dot its surface like scars from the solar system's violent youth, each one a reminder of the cosmic bombardment that helped shape all the rocky planets billions of years ago. In the gentle darkness behind your eyelids, you might envision those early spacecraft making their lonely journeys across the void, carrying humanity's first close look at another world. Think of the scientists and engineers who dedicated their lives to these robotic explorers, knowing they would never walk on Martian soil themselves, but driven by an insatiable curiosity to understand our planetary neighbor. Their patient work, spanning decades and overcoming countless technical challenges, would gradually reveal Mars not as the Earth-like world of early speculation, nor as the utterly barren wasteland of first impressions, but as something far more intriguing. A world that was once more Earth-like than we ever imagined, and that might still hold secrets we're only beginning to uncover. Tonight, as you prepare for sleep, Mars continues its ancient orbit around the Sun, sometimes approaching as close as 35 million miles to Earth, sometimes receding to more than 200 million miles away. At this very moment, robotic rovers are trundling across its surface, analyzing rocks and soil, searching for signs of past or present life, and slowly, patiently, adding new chapters to the story of the red planet. As we drift deeper into the story of Mars, we find ourselves drawn to the remarkable ways this distant world has revealed its secrets to us across the centuries. The same red wanderer that puzzled ancient astronomers continues to surprise us today, each new discovery adding another layer to our understanding of this complex and fascinating neighbor. In those early telescopic observations we mentioned, astronomers noticed something peculiar about Mars that set it apart from other planets. Unlike the steady, predictable movements of Venus or Jupiter, Mars seemed to perform a strange dance across the night sky. For months, it would move steadily eastward against the background stars, then suddenly slow down, stop, and begin moving backward for several weeks before resuming its forward journey. This retrograde motion, as it came to be known, seemed almost magical, defying the orderly movements expected of celestial bodies. The explanation for this cosmic choreography is actually quite elegant, though it took centuries to understand fully. Mars appears to move backward, not because it actually reverses direction, but because of the relative motion between Earth and Mars as they orbit the Sun at different speeds. Imagine two runners on a circular track, with the inner runner moving faster than the outer one. As the faster inner runner overtakes the slower outer runner, there's a moment when the outer runner appears to be moving backward relative to the inner runner's perspective. This is precisely what happens when Earth, traveling in its smaller, faster orbit, overtakes Mars in its larger, slower orbit around the Sun. This dance of the planets occurs roughly every 26 months, when Earth and Mars align in what astronomers call opposition. During these close approaches, Mars appears larger and brighter in our sky, making it the ideal time for observation and, in our modern era, for launching spacecraft to the red planet. These opposition periods have been crucial to our understanding of Mars, providing windows of opportunity that have shaped centuries of Martian exploration. The early telescopic observers made the most of these opposition periods, carefully mapping what they could see of the Martian surface. They discovered that Mars has seasons much like Earth, watching as white polar caps grew and shrank with the changing Martian year. They observed dust storms that could engulf the entire planet, turning the red world into a featureless orange sphere for months at a time. Most intriguingly, they documented the appearance and disappearance of dark markings across the planet's surface, features that seemed to change with the seasons. These seasonal changes sparked some of the most romantic theories in the history of astronomy. As the polar caps shrank during the Martian spring and summer, dark lines appeared to spread across the planet's surface. To many observers, this suggested a world where melting ice caps released water that flowed through vast canal systems, supporting the growth of vegetation that darkened the landscape. The idea of a living, breathing Mars captured imaginations around the world and fueled countless stories of Martian civilizations. The Italian astronomer Giovanni Schiaparelli played a particularly important role in developing these ideas. During the favorable opposition of 1877, he created detailed maps of Mars that showed numerous linear features crisscrossing the planet's surface. He called these features canali, which simply means channels in Italian, but when translated into English as canals, the word carried implications of artificial construction. This linguistic accident helped fuel speculation about Martian engineering projects on a planetary scale. American astronomer Percival Lowell embraced and expanded upon these ideas with remarkable enthusiasm. From his observatory in Arizona, Lowell spent years studying Mars and became convinced that the canal networks were evidence of a dying civilization's desperate attempt to transport water from the polar regions to the equatorial deserts. He envisioned an ancient, noble race of Martians engaged in a planet-wide engineering project to save their world from desiccation. Lowell's passionate advocacy for Martian intelligence influenced popular culture for decades and inspired countless works of science fiction. Yet even as these romantic visions of Mars captured public imagination, other astronomers were beginning to question the canal observations. The linear features that seemed so obvious to some observers remained stubbornly invisible to others, even when using telescopes of similar quality. This discrepancy suggested that the canals might be optical illusions, tricks of the eye and brain that transformed random surface markings into geometric patterns when viewed at the limits of telescopic resolution. The debate over Martian canals continued well into the 20th century, with passionate advocates on both sides presenting careful observations and detailed arguments. Some astronomers remained convinced that they were seeing real surface features, while others insisted that the canals were merely artifacts of poor atmospheric conditions and the human tendency to perceive patterns where none existed. This controversy highlighted the challenges of astronomical observation and the importance of maintaining scientific skepticism even in the face of exciting possibilities. As telescopic technology improved and observing techniques became more sophisticated, the canal networks gradually faded from view. Modern photographs taken through Earth-based telescopes show no trace of the linear features that once seemed so prominent to earlier observers. The seasonal changes that had been attributed to growing vegetation were revealed to be dust storms and shifting surface materials responding to temperature changes and atmospheric circulation patterns. This gradual dissolution of the canal theory represents one of astronomy's most important lessons about the difference between observation and interpretation. The early telescopic observers were not deceiving themselves or others. They were genuinely reporting what they thought they saw through their instruments. However, they were working at the very limits of their technology's capabilities, trying to discern fine details on a distant world through the turbulent atmosphere of Earth. Under such challenging conditions, the human brain's pattern recognition systems can create the illusion of structure and organization where none actually exists. The story of the Martian canals also illustrates how scientific theories can be influenced by the cultural context in which they develop. The late 19th and early 20th centuries were periods of tremendous engineering achievement on Earth, with the construction of major canal systems like the Suez and Panama canals demonstrating humanity's ability to reshape landscapes on a massive scale. In this context, the idea of an even more advanced civilization undertaking similar projects on Mars seemed not only plausible, but almost inevitable. Despite the eventual debunking of the canal theory, these early observations of Mars were far from worthless. The careful mapping and documentation of seasonal changes provided crucial information about Martian weather patterns, atmospheric composition, and surface properties. The detailed drawings and measurements made during opposition periods created a baseline for understanding how Mars appears from Earth and helped establish the planet's basic physical characteristics. Moreover, the controversy over Martian canals had an important positive effect on the development of planetary astronomy. It demonstrated the need for multiple independent observations, careful documentation of observing conditions, and healthy skepticism about extraordinary claims. These lessons helped establish the rigorous observational standards that would prove essential when spacecraft finally began visiting Mars in the 1960s. The transition from telescopic speculation to spacecraft exploration marked a revolutionary change in our understanding of Mars. Where ground-based observers had been limited to studying the planet's overall appearance and seasonal changes, robotic explorers would soon be able to examine individual rocks, analyze soil samples, and map the planet's surface with unprecedented detail. This technological leap would finally provide definitive answers to questions that had puzzled astronomers for centuries. As we prepare to explore these spacecraft discoveries in the continuing chapters of Mars exploration, it's worth reflecting on the patience and dedication of those early telescopic observers. Working night after night through often difficult conditions, they gradually assembled the first scientific portrait of Mars as a real world, rather than merely a wandering point of light. Their work laid the foundation for everything that would follow, providing the context and motivation for the ambitious missions that would eventually carry our robotic ambassadors across the vast gulf of space to walk upon Martian soil. The red planet that had danced mysteriously across ancient skies was finally ready to reveal its true nature, though the revelations would prove to be quite different from what those early observers had imagined. By the late 1950s, as the space age dawned with the first artificial satellites, Mars transformed from a distant object of telescopic speculation into a tangible destination for human exploration. The red planet beckoned to engineers and dreamers alike, promising answers to questions that had tantalized humanity for centuries. Yet the journey from Earth to Mars would prove far more challenging than even the most pessimistic scientists had anticipated. The Soviet Union, emboldened by their early successes in space, launched the first mission toward Mars in October 1960. Mars 1M number 1, as it was designated, never made it beyond Earth's atmosphere. The rocket carrying this pioneering spacecraft exploded during launch, scattering the dreams of Martian exploration across the Siberian landscape. 3 days later, the Soviets tried again with Mars 1M number 2, only to witness another spectacular failure as the second stage of their launch vehicle malfunctioned. These early setbacks established a pattern that would haunt Mars exploration for decades. The red planet seemed to possess an almost supernatural ability to destroy the spacecraft sent to study it. Engineers began speaking in hushed tones about the Mars curse, or the great galactic ghoul that apparently devoured missions with alarming regularity. Of the first 10 missions launched toward Mars between 1960 and 1964, not a single one achieved complete success. The challenges were immense and varied. Mars orbits the Sun at a different rate than Earth, meaning launch windows occur only every 26 months when the planets align favorably. miss your window, and you wait over 2 years for another chance. The journey itself takes between 6 and 9 months, during which countless things can go wrong with delicate electronic systems exposed to the harsh radiation environment of interplanetary space. Communication delays stretch to over 20 minutes each way when Mars is at its farthest point from Earth, making real-time control impossible. Yet gradually, persistence began to pay dividends. In 1965, NASA's Mariner 4 became the first spacecraft to successfully fly by Mars and return images. The pictures it transmitted were crude by today's standards, showing a heavily cratered surface that resembled our moon more than the Earth-like world many had hoped to find. The atmospheric pressure was revealed to be less than 1% of Earth's, and temperatures were brutally cold. These findings dealt a severe blow to lingering hopes of finding complex life on Mars, but they also provided the first concrete scientific data about our planetary neighbor. The 1960s and early 1970s saw a steady stream of missions, with varying degrees of success. Mariner 6 and 7 provided additional flyby data in 1969, while the Soviet Mars 2 and 3 missions in 1971 attempted the first landings on the Martian surface. Mars 2 crashed, but Mars 3 achieved the first successful soft landing, though it transmitted for only 20 seconds before falling silent. The partial success was tantalizing, yet frustrating, offering just a glimpse of what might be possible. The breakthrough came with NASA's Mariner 9 mission, which arrived at Mars in November 1971 to become the first artificial satellite of another planet. Initially, the spacecraft found itself staring down at a planet-wide dust storm that obscured virtually the entire surface. For weeks, Mariner 9 waited patiently in orbit as the dust gradually settled, revealing wonders that exceeded the wildest expectations of mission planners. As the Martian atmosphere cleared, enormous volcanic mountains emerged from the haze. Olympus Mons, a shield volcano 3 times taller than Mount Everest, dominated the Tharsis region. Vast canyon systems stretched across the surface, dwarfing Earth's Grand Canyon. Most intriguingly, Mariner 9 revealed what appeared to be dried riverbeds, suggesting that liquid water had once flowed across the Martian landscape. These discoveries revolutionized our understanding of Mars, transforming it from a static, moon-like world into a dynamic planet with a complex geological history. Building on these revelations, NASA launched the ambitious Viking program in 1975. Twin orbiters and landers were designed to conduct the most comprehensive study of Mars ever attempted. The Viking 1 lander touched down in Cresplanitya on July 20, 1976, exactly 7 years after the first moon landing. The images it transmitted showed a rocky, desert-like landscape under a butterscotch sky, alien yet strangely familiar. The Viking missions operated far beyond their planned lifespans, with some components functioning for years. They mapped the planet in unprecedented detail, analyzed soil samples, monitored weather patterns, and conducted the first dedicated search for life on another planet. The biological experiments produced tantalizing, but ultimately inconclusive results. Some tests suggested metabolic activity in the Martian soil, while others failed to detect the organic compounds that would be expected if life were present. The scientific community remained divided, with most researchers concluding that the results could be explained by unusual soil chemistry rather than biology. Despite the ambiguous biological results, Viking established Mars as a world of incredible complexity and beauty. The missions revealed seasonal changes as carbon dioxide froze and sublimated at the polar caps, dust devils dancing across the plains, and morning frost forming in sheltered areas. Mars emerged as a world with weather, seasons, and daily cycles not entirely unlike Earth's, yet profoundly different in ways that challenged our understanding of planetary evolution. After Viking, budget constraints and technical challenges led to a lengthy hiatus in Mars exploration during the 1980s. Several missions were planned but cancelled, while others ended in failure. The Soviet Phobos missions of the late 1980s suffered technical problems, with Phobos 1 lost en route to Mars and Phobos 2 failing just before reaching its target, the Martian moon Phobos. NASA's Mars Observer, launched in 1992, disappeared just 3 days before arriving at Mars, adding another victim to the growing list of failed missions. The 1990s marked a renaissance in Mars exploration, driven by new technologies, renewed scientific interest, and a shift towards smaller, more focused missions. NASA's faster, better, cheaper philosophy led to the development of spacecraft that could be built and launched more frequently, reducing the impact of individual failures while increasing the overall pace of discovery. Mars Pathfinder, launched in 1996, demonstrated revolutionary new landing techniques and deployed the first successful Mars rover, a small, six-wheeled vehicle named Sojourner. The mission captivated public attention as images of the tiny rover exploring the Martian landscape appeared on the internet, which was just becoming widely accessible. Sojourner's success proved that mobile exploration of Mars was feasible and set the stage for increasingly ambitious rover missions. The twin Mars exploration rovers, Spirit and Opportunity, launched in 2003, were designed to operate for 90 Martian days, but exceeded all expectations. Spirit functioned for over 6 years, while Opportunity operated for nearly 15 years, transforming our understanding of Martian geology and climate history. These rovers found compelling evidence that liquid water had once been abundant on Mars, analyzing minerals that could only have formed in the presence of water, and discovering geological formations consistent with ancient lake beds and river deltas. As the new millennium progressed, Mars exploration entered an era of unprecedented sophistication. The Mars Reconnaissance Orbiter, launched in 2005, carried the most powerful camera ever sent to another planet, capable of resolving objects as small as a desk from orbit. Its images revealed Mars in stunning detail, showing everything from avalanches cascading down cliff faces to dust devils tracked across the landscape over time. The Curiosity rover, which landed in 2012, represented a quantum leap in capability. The size of a small car and powered by a nuclear generator, Curiosity carried a sophisticated laboratory capable of analyzing rock and soil samples with unprecedented precision. Its landing system, dubbed the Sky Crane, seemed like science fiction made real as rocket-powered platforms lowered the rover to the surface on cables. Curiosity's discoveries have been profound. The rover found evidence of ancient lake beds in Gale Crater, analyzed organic compounds in Martian rocks, and detected seasonal variations in atmospheric methane that hint at ongoing geological or possibly biological processes. Each discovery adds another piece to the complex puzzle of Martian history and evolution. Today, Mars hosts an international fleet of robotic explorers. NASA's Perseverance rover searches for signs of ancient microbial life while preparing samples for eventual return to Earth. The Ingenuity helicopter has demonstrated powered flight in Mars' thin atmosphere, opening new possibilities for aerial exploration. China's Tianwen-1 mission successfully placed both an orbiter and rover on Mars, while the United Arab Emirates Hope probe studies the Martian atmosphere from orbit. These modern missions reveal Mars as a world of extraordinary complexity and beauty. High-resolution images show landscapes that range from familiar-looking desert vistas to utterly alien terrain sculpted by processes unknown on Earth. Seasonal changes create dynamic patterns as frost advances and retreats across the polar regions. Ancient impact craters preserve records of the solar system's violent early history, while younger volcanic features suggest that Mars remained geologically active longer than previously thought. The search for life continues to drive Mars exploration, but it has evolved beyond simple questions of whether life exists to more nuanced investigations of habitability and preservation. Scientists now understand that if life ever arose on Mars, it likely retreated underground as the planet's atmosphere thinned and surface conditions became increasingly harsh. Future missions will drill deeper into the Martian subsurface, seeking protected environments where life might persist, or where biosignatures might be preserved in ancient rocks. As you settle into sleep tonight, consider the remarkable journey from those first telescopic glimpses of a wandering red star to today's sophisticated robotic explorers roving across alien landscapes. In just over a century, Mars has been transformed from a mysterious light in the sky to a world we know in intimate detail, a place where human footprints may soon join the tracks left by our mechanical ambassadors. Looking at Mars, we find ourselves at the threshold of understanding a world that has undergone one of the most dramatic transformations in our solar system. The story of Martian climate is not just about planetary science. It's about the delicate balance of forces that determine whether a world can sustain the conditions necessary for life as we know it. Billions of years ago, Mars was a fundamentally different place than the cold, dry world we observe today. Evidence scattered across its surface tells the story of a planet that once possessed a thick atmosphere, flowing rivers, and perhaps even vast oceans. Ancient riverbeds carved deep into the Martian landscape speak of water that flowed for millions of years. Deltas preserved in sedimentary rock reveal where rivers once emptied into larger bodies of water. Mineral deposits that can only form in the presence of liquid water dot the planet's surface like geological breadcrumbs, leading us back to a warmer, wetter past. The transformation of Mars from this potentially habitable world to its current state represents one of the most significant climate changes we can study in our solar system. Understanding how and why this transformation occurred provides crucial insights not only into Martian history, but also into the broader question of planetary habitability and the factors that govern long-term climate stability. The key to Mars's dramatic climate change lies in the interplay between several fundamental planetary characteristics. Unlike Earth, Mars is a smaller world with only about half our planet's diameter and roughly 11% of Earth's mass. This smaller size had profound consequences for the planet's ability to retain its atmosphere and maintain the geological processes that help regulate climate over long timescales. The reduced gravitational pull on Mars meant that atmospheric gases could more easily escape to space, particularly when energized by solar radiation or impacts from asteroids and comets. The planet's smaller size also meant that its interior cooled more rapidly than Earth's, leading to the cessation of the global magnetic field that once protected Mars from the solar wind. Without this magnetic shield, charged particles from the Sun could directly interact with the Martian atmosphere, gradually stripping it away over geological time. The story begins in what planetary scientists call the Noachian period, named after the heavily cratered terrain that preserves evidence of Mars' earliest history. During this epoch, which lasted from the planet's formation about 4.5 billion years ago until roughly 3.5 billion years ago, Mars likely possessed a substantial atmosphere composed primarily of carbon dioxide, with significant amounts of water vapor and other gases. This early atmosphere was thick enough to create a greenhouse effect that could maintain liquid water on the surface, despite Mars's greater distance from the Sun. The planet received only about 43% of the solar energy that Earth receives, but the thick carbon dioxide atmosphere trapped enough heat to keep surface temperatures above the freezing point of water across much of the planet. Evidence for this warmer climate comes from numerous sources. Valley networks that snake across the ancient Martian highlands show clear signs of erosion by flowing water. These features are not the result of catastrophic flooding, but rather the patient work of rivers that flowed for extended periods, carving channels and transporting sediment just as rivers do on Earth today. The branching patterns of these valley networks, their gradual downstream widening, and the presence of tributary systems all point to sustained hydrological activity. Perhaps even more compelling are the mineralogical signatures preserved in ancient Martian rocks. Clays, sulfates, and other hydrated minerals detected by orbiting spacecraft and analyzed by rovers on the surface require liquid water for their formation. The specific types of minerals found in different regions tell us not just that water was present, but also about the chemistry and pH of that ancient water, painting a picture of diverse aquatic environments that persisted for millions of years. The northern lowlands of Mars present another intriguing piece of evidence for ancient water. These vast, relatively smooth plains sit several kilometers below the average elevation of the planet and show characteristics that some researchers interpret as ancient ocean basins. If correct, this would suggest that Mars once possessed a northern ocean covering roughly 1/3 of the planet's surface, with a volume comparable to Earth's Arctic Ocean. The transition away from this warmer, wetter climate began during what geologists call the Hesperian period, roughly 3.5 to 3 billion years ago. This era marked the beginning of Mars' transformation into the cold, dry world we know today, though the process was gradual and complex, with periods of renewed volcanic activity and occasional returns to warmer conditions. Several factors contributed to this climate transition. The gradual loss of atmospheric mass meant that the greenhouse effect weakened over time, making it increasingly difficult to maintain liquid water on the surface. As the atmosphere thinned, water began to freeze and sublime directly from ice to vapor, further reducing atmospheric pressure and accelerating the cooling process. The loss of Mars's global magnetic field, which probably occurred sometime during the first billion years of the planet's history, removed a crucial protection against atmospheric loss. Earth's magnetic field deflects most of the charged particles in the solar wind, but without this shield, Mars became vulnerable to atmospheric stripping. High-energy particles from the Sun could directly impact atmospheric molecules, giving them enough energy to escape the planet's gravitational pull. Volcanic activity also played a complex role in Mars' climate evolution. While volcanic outgassing could replenish atmospheric gases lost to space, the pattern of Martian volcanism was different from Earth's. Rather than the continuous recycling of crustal material through plate tectonics, Mars developed a few massive volcanic provinces that were active for extended periods, but eventually went dormant. The largest of these, the Tharsis volcanic province, contains some of the most massive volcanoes in the solar system, including Olympus Mons, which rises more than 21 kilometers above the surrounding terrain. The formation of Tharsis itself may have contributed to climate change on Mars. The enormous mass of this volcanic region, equivalent to roughly 1% of the planet's total mass, actually shifted Mars's axis of rotation over geological time. This process, called true polar wander, relocated the planet's ice caps and altered global circulation patterns, potentially affecting the stability of water and carbon dioxide reservoirs. As Mars cooled and its atmosphere thinned, water began to migrate from the surface to other reservoirs. Some froze into polar ice caps, which we can observe today as layered deposits of water ice and carbon dioxide ice at both poles. Other water became locked in permafrost beneath the surface, where it remains today in vast quantities. Estimates suggest that if all the water currently frozen in Martian soil were melted and distributed evenly across the planet's surface, it would create a global ocean several meters deep. The seasonal behavior of Mars today provides a window into the dynamic processes that continue to shape its climate. Each Martian year, roughly equivalent to 2 Earth years, we observe dramatic changes as carbon dioxide freezes out of the atmosphere at the winter pole and sublimes back into the atmosphere at the summer pole. This process is so efficient that it temporarily removes up to 30% of the planet's thin atmosphere, causing measurable changes in atmospheric pressure across the entire planet. These seasonal cycles also drive powerful dust storms that can engulf the entire planet for months at a time. The dust lifted into the atmosphere absorbs sunlight and can temporarily warm the planet, but it also blocks sunlight from reaching the surface, creating complex feedback effects on temperature and atmospheric circulation. Understanding these modern processes helps scientists model how similar but more intense processes might have operated when Mars had a thicker atmosphere. The search for evidence of life on Mars is intimately connected to understanding the planet's climate history. The period when Mars was warm and wet coincides with the time when life was becoming established on Earth, raising the tantalizing possibility that life might have emerged on Mars as well. Even after the planet's climate changed, life might have persisted in subsurface environments where liquid water could still exist, protected from the harsh surface conditions by layers of rock and soil. Recent discoveries have added new chapters to the story of Martian climate. The detection of methane in the Martian atmosphere, though controversial and still debated, could indicate either ongoing geological processes or even biological activity. Seasonal variations in atmospheric methane, if confirmed, would suggest active sources and sinks for this gas, implying that Mars is not the geologically dead world it was once thought to be. The discovery of recurring slope lineae, dark streaks that appear seasonally on steep slopes in warm regions of Mars, initially sparked excitement as possible evidence of liquid water flowing on the modern Martian surface. While subsequent analysis suggests these features are more likely caused by dry granular flows, they highlight the ongoing dynamic processes that continue to shape the planet's surface. Understanding Mars's climate history also has profound implications for the possibility of future human exploration and eventual settlement. The planet's climate is not static, but continues to evolve, albeit slowly. Long-term cycles in Mars's orbit and axial tilt, similar to the Milankovitch cycles that drive ice ages on Earth, cause significant changes in the distribution of solar heating and the stability of ice deposits. During periods of high obliquity, when Mars' axis is tilted more extremely than today, the polar ice caps can become unstable, releasing water vapor and carbon dioxide into the atmosphere and temporarily thickening it. These orbital cycles suggest that Mars undergoes periodic climate oscillations, with the planet becoming somewhat more hospitable during certain phases. Some researchers have proposed that these cycles might provide windows of opportunity for life to emerge from subsurface refugia and temporarily colonize the surface before retreating underground as conditions become harsh again. The story of Martian climate also serves as a cautionary tale about planetary habitability. Mars demonstrates that having liquid water on a planet's surface is not a permanent condition, but rather a delicate balance that depends on numerous factors, including atmospheric composition, planetary mass, magnetic field strength, and orbital characteristics. The loss of habitability on Mars was not a sudden catastrophe, but a gradual process that unfolded over hundreds of millions of years. This perspective has important implications for our understanding of exoplanets and the search for life beyond our solar system. Many of the potentially habitable exoplanets discovered by telescopes like Kepler and TESS are smaller than Earth, more similar in size to Mars. Understanding how Mars lost its habitability helps us evaluate the long-term prospects for life on these distant worlds and refine our definitions of what makes a planet truly habitable over geological timescales. As robotic missions continue to explore Mars and future human missions edge closer to reality, our understanding of Martian climate continues to evolve. Moving deeper into our exploration of Mars, we encounter one of the most profound questions that has captivated scientists and dreamers alike for generations. Could life exist on the red planet? The search for life on Mars represents perhaps the most ambitious chapter in our ongoing relationship with this distant world, transforming our understanding from speculation to systematic scientific investigation. The question of Martian life has evolved dramatically since the early telescopic observations that sparked tales of canals and civilizations. Today's search is far more nuanced, focusing not on little green beings, but on the fundamental building blocks of life itself. Organic molecules, water, and the chemical signatures that might indicate biological processes, either past or present. Our modern hunt for life on Mars operates on multiple fronts, each more sophisticated than early astronomers could have imagined. Orbiting spacecraft scan the planet's surface with instruments capable of detecting mineral compositions from hundreds of kilometers above. These orbital sentinels have identified clay minerals, sulfates, and other compounds that form in the presence of water, creating detailed maps of where life might once have taken hold or could potentially exist today. On the surface, our robotic explorers have become increasingly sophisticated biological detectives. The Curiosity rover, which landed in Gale Crater in 2012, carries an entire laboratory designed to analyze Martian rocks and soil for organic compounds. Its sample analysis at Mars instrument can heat rock samples to hundreds of degrees and analyze the resulting gases, searching for the carbon-based molecules that form the foundation of life as we know it. The results have been both tantalizing and complex. Curiosity has indeed detected organic molecules in Martian rocks, but their origin remains ambiguous. These compounds could represent the remnants of ancient life, or they might have formed through purely geological processes. Some could even have arrived from space, delivered by meteorites or comets over billions of years. The challenge lies not in finding organic molecules, but in determining their source. More recent missions have pushed the boundaries of life detection even further. The Perseverance rover, which began its mission in 2021, represents our most advanced attempt yet to answer the life question. Landing in Jezero Crater, a location chosen specifically for its geological history as an ancient lake bed, Perseverance carries instruments designed not just to detect organic compounds, but to search for biosignatures, the subtle chemical fingerprints that life leaves behind. The concept of biosignatures reflects our growing understanding of how life interacts with its environment. Living organisms don't exist in isolation. They alter their surroundings in characteristic ways. They consume certain chemicals and produce others, create specific isotopic ratios, and sometimes leave behind physical structures that betray their biological origin. On Earth, we can find evidence of life that existed billions of years ago, preserved in ancient rocks, and scientists hope that Mars might have preserved similar records. One of the most intriguing aspects of the search for Martian life involves methane, a simple molecule that has generated considerable excitement and controversy. Several missions have detected trace amounts of methane in the Martian atmosphere, but these detections have been sporadic and difficult to confirm. On Earth, most atmospheric methane is produced by living organisms, leading to speculation that Martian methane might indicate active biological processes. However, methane can also be produced by geological processes, and Mars presents unique challenges for methane detection. The thin atmosphere and intense solar radiation create conditions where methane should be destroyed relatively quickly, meaning that any methane detected must have been produced recently. This has led to a scientific puzzle. If methane is being produced on Mars, what is creating it, and why do we only detect it sometimes? The search for life has also led us to consider environments on Mars that might be habitable today. While the surface appears harsh and seemingly sterile, conditions beneath the ground could be more hospitable. liquid water might exist in underground aquifers, protected from radiation and extreme temperature variations. Some scientists speculate that if life exists on Mars today, it might be found in these subsurface environments, possibly surviving in ways similar to extremophile organisms found deep underground on Earth. The discovery of seasonal changes in atmospheric methane concentrations has added another layer to this mystery. If these variations are real, they suggest active processes that operate on timescales much shorter than geological ones. Some researchers have proposed that these seasonal patterns could indicate biological activity that waxes and wanes with Martian seasons, though purely chemical explanations remain equally plausible. Our understanding of where to look for life on Mars has been shaped by discoveries about life on Earth in extreme environments. Scientists have found organisms thriving in conditions once thought impossible for life. In boiling hot springs, extremely acidic waters, deep underground with no sunlight, and in environments with high levels of radiation. These discoveries have expanded our definition of habitability and suggested that Mars might have more potentially habitable environments than previously thought. The search has also been informed by studies of Mars meteorites found on Earth. These rocks, blasted from Mars by ancient impacts and eventually falling to Earth, provide direct samples of Martian material that can be studied in terrestrial laboratories with the most sophisticated instruments available. Some of these meteorites have yielded intriguing results, including microscopic structures that some scientists interpret as possible fossilized microorganisms, though these claims remain highly controversial. The question of past versus present life on Mars represents one of the fundamental challenges in astrobiology. Evidence suggests that early Mars had conditions that might have been suitable for life: liquid water, a thicker atmosphere, and active geology that could have provided energy sources. However, these conditions changed dramatically as Mars lost much of its atmosphere and surface water. The question becomes whether life, if it ever existed, could have adapted to these changing conditions or found refuge in protected environments. Recent missions have focused increasingly on understanding the habitability of ancient Martian environments. By studying the geological record preserved in Martian rocks, scientists can reconstruct the conditions that existed billions of years ago and assess whether they could have supported life. This approach has revealed that early Mars likely had diverse environments, from alkaline lakes to acidic hot springs, each of which might have provided different opportunities for life to emerge and evolve. The search for life has also driven technological innovation, pushing the boundaries of what's possible in robotic exploration. Future missions are planned to return samples from Mars to Earth, where they can be analyzed with instruments far more sophisticated than anything that can be sent to Mars. This sample return mission represents a crucial next step in the search for life, potentially providing definitive answers to questions that current missions can only address indirectly. As we continue this search, we're forced to confront fundamental questions about the nature of life itself. Our search strategies are necessarily based on life as we know it, focusing on carbon-based chemistry and liquid water. But could life on Mars have evolved along different pathways, using different chemistry, or existing in states we haven't yet imagined? These questions push us to think more broadly about what life might look like and how we might recognize it. The implications of discovering life on Mars, whether past or present, would be profound. It would suggest that life might be more common in the universe than we currently understand, arising independently on at least 2 worlds in our own solar system. Conversely, if we eventually conclude that Mars never harbored life, despite apparently favorable conditions, that too would tell us something important about the requirements for life and its likelihood elsewhere in the cosmos. As our robotic explorers continue their patient work on the Martian surface, analyzing samples and transmitting data across the vast distance to Earth, we edge closer to answering one of humanity's most enduring questions. whether Mars once teemed with microscopic life in its ancient lakes and rivers, whether life persists today in hidden underground refuges, or whether Mars has always been sterile despite its apparent potential for habitability, the answer will reshape our understanding of life's place in the universe and our own significance as living beings contemplating the cosmos. The quest to understand Mars has now taken us beyond the realm of speculation and into the age of direct exploration. As we drift deeper into our Martian journey tonight, we find ourselves at a fascinating crossroads where human ingenuity meets the harsh realities of interplanetary travel. The same red dot that captivated ancient astronomers has become humanity's most thoroughly studied celestial neighbor, revealing secrets that continue to reshape our understanding of planetary evolution and the potential for life beyond Earth. Following the groundbreaking discoveries of the early robotic missions, the pace of Martian exploration began to accelerate in ways that would have seemed impossible to those first telescope observers. The Viking missions of 1976 represented a quantum leap in our capabilities, marking the first successful American landings on the Martian surface. These twin spacecraft, each consisting of an orbiter and lander, were designed to search for signs of life while providing unprecedented detail about Mars's atmosphere, weather, and geology. The Viking landers touched down on opposite sides of Mars, beginning what would become humanity's longest-running extraterrestrial field study. For years, these robotic explorers transmitted images of a world that was simultaneously alien and strangely familiar. The Martian landscape revealed itself to be a place of rust-colored plains, ancient impact craters, and towering volcanic formations that dwarfed anything found on Earth. The cameras captured dust devils dancing across the surface, seasonal changes in the polar ice caps, and the gradual accumulation of fine particles that would occasionally coat the spacecraft in layers of Martian dust. Perhaps most intriguingly, the Viking missions carried sophisticated instruments designed to detect signs of microbial life in the Martian soil. The results of these biological experiments remain controversial to this day, with some researchers arguing that the data showed chemical signatures consistent with living organisms, while others maintained that the results could be explained by purely geological processes. This ambiguity only deepened the mystery surrounding Mars and its potential for harboring life. The atmospheric studies conducted by Viking revealed a world caught between two states of being. Mars possesses a thin atmosphere composed primarily of carbon dioxide, with traces of nitrogen and argon. The atmospheric pressure at the surface is less than 1% of Earth's, creating conditions where liquid water cannot exist stably under normal circumstances. Yet the presence of water vapor in the atmosphere, combined with the obvious signs of ancient water activity carved into the planet's surface, suggested that Mars had once been a very different world. Temperature measurements painted a picture of a planet locked in perpetual cold. Even during the warmest summer days at the equator, temperatures rarely climb above freezing, while winter nights can plunge to minus 125 degrees Celsius. These extreme temperature variations, combined with the thin atmosphere, create weather patterns that are both familiar and alien. Dust storms can engulf the entire planet for months at a time, while morning frost forms and evaporates with the rising sun in a daily cycle that has continued for billions of years. The geological revelations from Viking and subsequent missions gradually unveiled Mars as a world of unprecedented extremes. Olympus Mons, the largest volcano in the solar system, rises nearly 25 kilometers above the surrounding plains, its base covering an area roughly the size of France. This massive shield volcano speaks to a geological history far more dramatic than Earth's, suggesting that Mars once possessed the internal heat and geological activity necessary to build such enormous structures. Equally impressive is Valles Marineris, a canyon system that stretches over 4,000 kilometers across the Martian equator. This vast scar in the planet's surface is so large that it could span the entire continental United States, reaching depths of up to 7 kilometers in some places. The formation of this canyon system remains one of Mars's great geological mysteries, with theories ranging from tectonic activity to massive water outflows, or even the gradual collapse of underground cavern systems. As the decades passed and technology advanced, new missions continued to refine our understanding of Mars while raising new questions about its past and present. The Mars Global Surveyor, launched in 1996, provided the first comprehensive global maps of Mars using laser altimetry and high-resolution cameras. These detailed topographical maps revealed a planet divided into two distinct hemispheres: the northern lowlands, which appear to be relatively young and smooth, and the southern highlands, which are heavily cratered and ancient. This hemispheric dichotomy represents one of the most fundamental puzzles in Martian geology. The northern plains lie several kilometers lower than the southern highlands, creating what appears to be a massive impact basin that covers nearly half the planet. Some researchers propose that this feature resulted from a catastrophic impact early in Mars's history, when an object roughly the size of Earth's moon struck the planet with enough force to reshape its entire surface. Others suggest that the dichotomy formed through internal geological processes that we don't yet fully understand. The search for water on Mars has remained a central theme throughout decades of exploration. While the planet's surface appears dry and barren today, the evidence for past water activity becomes more compelling with each new mission. High-resolution images reveal networks of valleys that bear striking resemblances to river systems on Earth, complete with tributaries, meanders, and delta formations, where ancient rivers once emptied into long-vanished lakes or seas. Perhaps most tantalizing are the recurring slope lineae, dark streaks that appear seasonally on certain Martian slopes. These features, first discovered by the Mars Reconnaissance Orbiter, appear to flow downhill during warm seasons and fade during colder periods. The seasonal nature of these features, combined with their flow-like appearance, suggests that they may be caused by briny water that becomes liquid during Mars's warmest periods, only to freeze or evaporate as conditions change. The discovery of subsurface ice deposits across much of Mars has revolutionized our understanding of the planet's water resources. Radar instruments aboard orbiting spacecraft have detected vast quantities of water ice buried beneath the surface, particularly in the polar regions. These ice deposits, some of which lie just meters below the surface, represent a potential resource that could support future human exploration while providing clues about Mars's climatic history. The Phoenix lander, which touched down in the Martian Arctic in 2008, provided direct confirmation of subsurface ice when its robotic arm excavated trenches that revealed bright white material that sublimated away in the thin Martian atmosphere. Chemical analysis of the soil revealed the presence of perchlorates, highly oxidizing chemicals that could potentially support certain types of microbial life, while simultaneously making the surface environment hostile to most Earth-based organisms. As our robotic emissaries continued their patient exploration of Mars, they began to uncover evidence of the planet's complex atmospheric evolution. The MAVEN mission, designed specifically to study Mars's upper atmosphere, revealed how the planet gradually lost much of its original atmosphere to space. Without a strong magnetic field to protect it from the solar wind, Mars has been slowly bleeding its atmosphere away for billions of years, transforming from a world that may once have supported liquid water on its surface to the cold, dry desert we observe today. The implications of this atmospheric loss extend far beyond mere scientific curiosity. Understanding how Mars lost its atmosphere provides crucial insights into planetary habitability and the factors that determine whether a world can maintain conditions suitable for life over geological timescales. The story of Mars serves as both a cautionary tale and a guide for understanding the delicate balance of factors that have allowed Earth to remain habitable for billions of years. Throughout this long process of exploration and discovery, Mars has gradually transformed from a mysterious red wanderer into a complex world with its own unique history and character. Each new mission has added layers to our understanding while revealing new mysteries that demand further investigation. The planet that once seemed like a simple, moon-like world has revealed itself to be a dynamic, evolving system with active geology, changing seasons, and the tantalizing possibility that life may have once existed, or perhaps still exists, beneath its seemingly barren surface. As we continue our gentle journey through the science of Mars, let your mind wander across those ancient riverbeds and towering volcanoes, through the thin atmosphere where dust storms rage and morning frost forms, and down into the subsurface realms, where ice and perhaps even life itself may wait to be discovered. The Martian atmosphere, a vanishing veil. Continuing our exploration of the red planet, we turn our attention to one of Mars's most defining characteristics: its remarkably thin atmosphere. This delicate envelope of gases tells a story of planetary transformation that spans billions of years, offering us glimpses into both Mars's dynamic past and its uncertain future. The Martian atmosphere, as we observe it today, is a gossamer-thin layer containing less than 1% of Earth's atmospheric pressure. Standing on the Martian surface, you would experience atmospheric pressure roughly equivalent to what you might find at an altitude of 35 kilometers above Earth's surface. This tenuous blanket consists primarily of carbon dioxide, making up about 96% of the total atmospheric composition. Nitrogen accounts for just under 2%, with argon comprising most of the remainder. Trace amounts of oxygen, water vapor, and other gases complete this sparse mixture. This atmospheric thinness has profound implications for conditions on Mars. Without a substantial atmosphere to trap heat through the greenhouse effect, surface temperatures fluctuate dramatically. During Martian summer, equatorial regions might see temperatures rise to a relatively pleasant 20 degrees Celsius during the day, only to plummet to minus 80 degrees Celsius at night. The lack of atmospheric density also means that even on the warmest Martian days, the air would feel intensely cold to human skin, as the thin atmosphere cannot effectively transfer heat. The story of how Mars came to possess such a tenuous atmosphere is one of gradual loss over geological time. Evidence suggests that early Mars maintained a much thicker atmosphere, one capable of supporting liquid water on its surface for extended periods. This ancient atmosphere likely contained significantly more carbon dioxide and water vapor, creating conditions that could have sustained a more temperate climate. The primary mechanism driving this atmospheric loss appears to be solar wind stripping. Unlike Earth, Mars lacks a strong global magnetic field to deflect the charged particles streaming from the Sun. Our planet's magnetic field acts as a protective shield, deflecting most solar wind particles and preventing them from directly interacting with our atmosphere. Mars, however, lost its global magnetic field relatively early in its history, likely within the first few 100 million years of its formation. Without this protective magnetic barrier, solar wind particles can penetrate deep into the Martian atmosphere, where they interact with atmospheric molecules through various processes. High-energy particles can knock atmospheric molecules out of Mars's gravitational grasp, allowing them to escape into space. Over billions of years, this continuous atmospheric erosion has transformed Mars from a world that might have resembled early Earth into the cold, dry planet we observe today. Recent missions have provided unprecedented insights into this ongoing atmospheric escape. The Mars Atmosphere and Volatile Evolution mission, known as MAVEN, has been monitoring the upper Martian atmosphere since 2014, measuring the rates at which different atmospheric components are lost to space. These observations have revealed that Mars continues to lose atmosphere today, though at a much slower rate than during its early history, when solar radiation was more intense. MAVEN's measurements indicate that Mars loses approximately 100 grams of atmosphere to space every second. While this might seem substantial, it represents only a tiny fraction of the planet's remaining atmospheric mass. During periods of high solar activity, however, this loss rate can increase dramatically, sometimes by an order of magnitude or more. This variability suggests that atmospheric loss rates in Mars's past, when the Sun was more active and the solar wind more intense, could have been significantly higher than what we observe today. The seasonal behavior of Mars's atmosphere adds another layer of complexity to our understanding. As winter approaches each Martian pole, temperatures drop sufficiently to freeze carbon dioxide directly from the atmosphere onto the polar ice caps. This process removes substantial amounts of atmospheric mass, causing measurable changes in global atmospheric pressure. During the southern winter, when the larger southern polar cap forms, atmospheric pressure can drop by as much as 25%. When spring returns, this frozen carbon dioxide sublimes directly back into the atmosphere, restoring much of the lost atmospheric mass. This seasonal breathing of the Martian atmosphere creates pressure waves that propagate around the planet and can be detected by sensitive instruments on Mars, orbiters, and surface missions. Water vapor, though present in only trace amounts, plays a crucial role in Martian atmospheric dynamics. The atmosphere can hold very little water vapor due to its thinness and cold temperatures, but what moisture exists participates in the formation of clouds, particularly during certain seasons and in specific geographical regions. These water ice clouds often form around the massive Martian volcanoes, where local topography forces atmospheric circulation patterns that promote cloud formation. Dust represents another significant component of the Martian atmospheric story. Fine particles of iron oxide and other minerals can be lifted into the atmosphere by wind action, sometimes creating dust storms that can envelop large portions of the planet or, in extreme cases, the entire globe. These dust storms can persist for weeks or months, dramatically altering atmospheric heating patterns and affecting weather systems across the planet. The interaction between atmospheric dust and solar radiation creates complex feedback loops that influence Martian climate. Airborne dust absorbs solar radiation and re-radiates it as heat, warming the atmosphere and potentially driving stronger winds that can lift even more dust into the air. During major dust storms, so much particulate matter becomes suspended in the atmosphere that the Martian sky can take on an orange or butterscotch hue and surface visibility can drop to just a few meters. These dust events have practical implications for Mars exploration missions. Solar-powered rovers and landers can see their power generation capabilities severely reduced during major dust storms, as airborne particles block sunlight from reaching their solar arrays. The 2018 global dust storm on Mars effectively ended the mission of the Opportunity rover, which had been operating on the Martian surface for nearly 15 years. Methane detection in the Martian atmosphere has generated considerable excitement in the scientific community. While present in extremely small concentrations, the detection of methane is significant because this molecule is relatively short-lived in the Martian environment. Its presence suggests either ongoing geological processes or potentially even biological activity, producing fresh methane to replace what is continuously being destroyed by chemical reactions in the atmosphere. The source of Martian methane remains one of the planet's most intriguing mysteries. On Earth, methane is produced both through biological processes and geological activity such as serpentinization, where water reacts with certain minerals to produce hydrogen and methane. Determining which process might be responsible for Martian methane production represents one of the key objectives for current and future Mars missions. Atmospheric chemistry on Mars involves complex interactions between trace gases and the planet's surface materials. The thin atmosphere allows ultraviolet radiation from the sun to penetrate to the surface with minimal filtering, driving photochemical reactions. that would be impossible under Earth's thicker atmospheric blanket. These reactions can produce highly reactive chemical species that interact with surface minerals, potentially creating the complex chemistry that future missions hope to study in detail. The study of Mars's atmospheric evolution provides valuable insights into planetary science more broadly. By understanding how Mars lost its atmosphere, scientists can better appreciate the factors that have allowed Earth to maintain its thick, life-sustaining atmosphere over geological time. This knowledge becomes increasingly important as we consider the habitability of exoplanets around other stars and the long-term stability of planetary atmospheres in general. Looking toward the future, the Martian atmosphere will continue its slow evolution. Atmospheric escape will persist, though at gradually decreasing rates as the remaining atmosphere becomes increasingly tenuous. Seasonal cycles will continue to drive the annual exchange of carbon dioxide between the atmosphere and polar ice caps. Dust storms will periodically reshape atmospheric dynamics and surface features. For future human missions to Mars, the thin atmosphere presents both challenges and opportunities. The low atmospheric density makes traditional parachute-based landing systems less effective, requiring innovative engineering solutions for safely delivering large payloads to the surface. However, the carbon dioxide-rich atmosphere could potentially be harvested and converted into oxygen for life support systems, or fuel for return journeys to Earth. As we continue to study Mars's atmosphere through ongoing and planned missions, each new observation adds another piece to the puzzle of planetary evolution. The story written in Mars's thin atmospheric veil speaks of a world transformed, offering lessons about the delicate balance required to maintain the atmospheric conditions that make planets habitable. Continuing from our exploration of Mars's atmospheric dynamics and ongoing research, we now turn our attention to one of the most intriguing aspects of Martian science: the search for signs of past and present life. This quest has driven much of our robotic exploration and continues to shape mission planning as we seek to answer one of humanity's most fundamental questions about our planetary neighbor. The search for life on Mars operates on multiple scales and approaches, from detecting biosignatures in ancient rocks to monitoring atmospheric gases that might indicate biological processes. Early telescopic observations sparked speculation about Martian life, with features like seasonal color changes and apparent linear structures fueling imagination about vegetation and even intelligent civilizations. However, our modern understanding has refined these ideas into more scientifically rigorous approaches, based on what we know about life's requirements and potential signatures. Water availability stands as the primary factor in assessing Mars's habitability potential. The planet's early history, when liquid water flowed across its surface and pooled in lakes and possibly oceans, represents the most promising period for life's emergence and evolution. During this time, Mars possessed many of the conditions we associate with habitability on Earth: liquid water, a thicker atmosphere providing greenhouse warming, and active geological processes that could have cycled nutrients and energy sources through the environment. The discovery of hydrated minerals across Mars's surface provides compelling evidence for these ancient aqueous environments. Clay minerals, or filler silicates, form only in the presence of liquid water and indicate prolonged interaction between water and rock. These minerals preserve chemical signatures of the conditions under which they formed, offering insights into ancient pH levels, temperature ranges, and the duration of water-rock interactions. Similarly, sulfate minerals suggest later periods when Mars's climate was becoming more acidic and arid, potentially concentrating salts and creating challenging but not impossible conditions for life. Organic molecules represent another crucial line of evidence in the search for Martian life. The Curiosity rover's detection of organic compounds in ancient mudstones within Gale Crater marked a significant milestone in this investigation. These carbon-containing molecules, while not definitive proof of life, demonstrate that the building blocks for biological processes were present on ancient Mars. The organic compounds discovered include both simple molecules like methane and more complex structures that could result from either biological or geological processes. The seasonal variation of methane in Mars's atmosphere adds another layer of intrigue to the life question. Earth's atmospheric methane comes predominantly from biological sources, though geological processes can also produce this gas through reactions between water and certain types of rock. Mars's methane appears to vary seasonally and spatially, suggesting active sources rather than ancient reservoirs slowly leaking into the atmosphere. Understanding these methane sources remains an active area of research, with implications for both geology and potential biology. Subsurface environments on Mars present some of the most promising targets for life detection. Radar observations have revealed extensive groundwater systems and possible liquid reservoirs beneath the polar ice caps. These subsurface environments would be protected from the harsh surface radiation, while potentially maintaining liquid water through geothermal heating or salt concentrations. On Earth, subsurface ecosystems thrive in similar conditions, deriving energy from chemical reactions rather than sunlight and surviving in environments previously thought uninhabitable. The concept of extremophiles has revolutionized our understanding of life's potential on Mars. These organisms thrive in conditions that would be lethal to most life forms, including high radiation, extreme temperatures, highly acidic or alkaline conditions, and environments with very low water activity. The discovery of life in Earth's most extreme environments, from deep ocean trenches to highly radioactive zones around nuclear reactors, has expanded the range of conditions we consider potentially habitable on other worlds. Perchlorate salts, abundant in Martian soil, initially seemed to present insurmountable challenges for life. These compounds are highly oxidizing and were thought to sterilize the surface environment. However, recent research has revealed that some Earth organisms can actually use perchlorates as energy sources, metabolizing them in ways that could potentially occur on Mars. This discovery transforms perchlorates from obstacles to life into possible resources for Martian organisms. The preservation of biosignatures presents unique challenges and opportunities on Mars. The planet's low atmospheric pressure and high radiation environment could degrade organic molecules and other signs of life at the surface over relatively short timescales. However, burial and mineralization processes could preserve these signatures for billions of years, creating a geological record of ancient life that might be more complete than what we find on Earth, where active tectonics and weathering continuously recycle rocks. Isotopic signatures offer another approach to detecting past life on Mars. Biological processes often preferentially use lighter isotopes of elements like carbon and sulfur, creating characteristic ratios that can persist in rocks long after the organisms themselves have disappeared. Future missions equipped with sensitive mass spectrometers will search for these isotopic fingerprints in carefully selected rock samples from environments most likely to have hosted life. The search for extant life focuses on environments where liquid water might exist today. Recurring slope lineae, dark streaks that appear and fade seasonally on steep slopes, were initially thought to indicate flowing briny water. While subsequent analysis suggests these features result from granular flows rather than liquid water, they highlight the ongoing search for active water processes that could support contemporary life. Deep subsurface environments remain largely unexplored, but represent perhaps the most likely refuges for present-day Martian life. Hydrothermal systems, if they exist, could provide both the energy and liquid water necessary for life. Geothermal gradients ensure that temperatures increase with depth, potentially maintaining liquid water even under current surface conditions. Accessing these environments presents significant technical challenges, but remains a priority for future exploration. The Mars Sample Return mission represents the next major step in the search for Martian life. By bringing carefully selected samples back to Earth, scientists will be able to apply the full range of analytical techniques available in terrestrial laboratories, including methods too complex and sensitive for deployment on robotic missions. These samples will undergo intensive analysis for organic compounds, isotopic signatures, mineral associations, and microscopic structures that might indicate biological origins. Contamination concerns work in both directions for Mars exploration. Forward contamination involves the potential introduction of Earth life to Mars, which could compromise our ability to detect indigenous Martian organisms or even establish itself in Martian environments. Backward contamination concerns the possibility that returned samples might contain viable Martian organisms that could affect Earth's biosphere. Strict planetary protection protocols govern both scenarios, requiring careful sterilization of outbound spacecraft and secure containment of returned samples. The implications of discovering life on Mars extend far beyond scientific curiosity. Such a discovery would represent the first confirmed example of life beyond Earth, fundamentally altering our understanding of biology's prevalence in the universe. If Martian life proved to be related to Earth life, it might suggest that life originated on one planet and spread to the other through meteorite transfer. Alternatively, if Martian life showed completely independent origins, it would suggest that life arises readily under suitable conditions, implying a universe potentially teeming with biological activity. As we continue this gentle exploration of Mars and its mysteries, the search for life remains central to our scientific objectives. Each rover tracks, each spectrometer reading, and each orbital observation contributes to our growing understanding of whether we are alone in our solar system or part of a larger community of living worlds. The search for life on Mars extends far beyond the simple question of whether microbes might exist in some hidden corner of the red planet. It reaches into the deepest mysteries of astrobiology, the study of life throughout the universe, and forces us to reconsider what we mean when we speak of habitability, adaptation, and the fundamental requirements for biological processes to unfold. As we drift deeper into this gentle exploration of Martian mysteries, let us consider the profound implications of what we have already discovered. The organic molecules detected by Curiosity and Perseverance rovers are not merely chemical curiosities scattered across an alien landscape. They represent potential building blocks, the molecular alphabet from which the story of life might be written. These carbon-based compounds, found preserved in ancient rocks and seasonal variations in the atmosphere, suggest that Mars once possessed, and may still possess, the chemical ingredients necessary for biological processes. The seasonal fluctuations of methane in Mars's thin atmosphere present one of the most intriguing puzzles in our ongoing investigation. On Earth, methane is produced primarily through biological processes, the metabolic byproducts of countless microorganisms living in environments ranging from deep ocean vents to the digestive systems of animals. The detection of methane plumes on Mars, appearing and disappearing with the changing seasons, raises tantalizing questions about what processes might be generating this gas on a world we have long considered geologically dormant. Yet the story grows more complex when we consider the geological processes that could also produce methane. Serpentinization, the chemical reaction between water and certain types of rock, can generate methane without any biological involvement. Subsurface volcanic activity, though currently undetected, could release trapped methane from ancient deposits. The challenge for astrobiologists lies in distinguishing between these geological sources and potential biological ones. a task that requires increasingly sophisticated analytical techniques and careful interpretation of data collected across multiple Martian years. The concept of biosignatures, those telltale traces that life leaves in its environment, has evolved considerably as our understanding of Mars has deepened. Early searches focused on obvious signs, structures that would clearly indicate the presence of past or present life. But the reality of detecting life on Mars may be far more subtle, requiring us to look for combinations of chemical, isotopic, and physical evidence that together paint a picture of biological activity. Consider the delicate dance of isotopes, those variations of elements that differ in atomic weight but share chemical properties. Life often preferentially uses lighter isotopes, leaving characteristic signatures in the materials it processes. The ratio of carbon-12 to carbon-13, the distribution of sulfur isotopes, the patterns of nitrogen incorporation, all of these could provide clues about biological processes operating on Mars, either in the distant past or in hidden environments today. The subsurface of Mars has emerged as perhaps the most promising frontier in our search for life. Beneath the harsh radiation and extreme temperature fluctuations of the surface lies a potentially more hospitable realm, where liquid water might persist, where temperatures remain more stable, and where any organisms would be shielded from the sterilizing effects of cosmic radiation and ultraviolet light from the sun. Recent discoveries have revealed that Mars possesses a surprisingly dynamic subsurface hydrological system. Ground-penetrating radar on orbiting spacecraft has detected what appear to be buried lakes beneath the polar ice caps. These subsurface bodies of liquid water, kept from freezing by dissolved salts and geothermal heat, could harbor microbial communities similar to those found in Earth's most extreme environments. The prospect of life existing in these hidden Martian lakes represents one of the most exciting possibilities in astrobiology. The study of extremophiles on Earth, organisms that thrive in conditions once thought impossible for life, has fundamentally changed our understanding of where life might exist on Mars. These remarkable organisms flourish in environments of extreme temperature, pressure, acidity, salinity, and radiation levels that would quickly prove fatal to most life forms. Some bacteria thrive in the highly acidic conditions of volcanic hot springs. Others survive in the intensely salty waters of hypersaline lakes, and still others endure the crushing pressures and complete darkness of deep ocean trenches. Perhaps most relevant to the Martian environment are the organisms that have adapted to high levels of radiation and extreme desiccation. Deinococcus radiodurans, sometimes called the most radiation-resistant organism known, can survive radiation levels thousands of times higher than would be lethal to humans. Desert-dwelling microbes have evolved mechanisms to survive extended periods without water, entering dormant states that can persist for years or even decades until conditions become favorable again. These discoveries on Earth suggest that if life ever arose on Mars, it might have found ways to persist, even as the planet's environment became increasingly hostile. The subsurface of Mars, with its potential for liquid water, protection from radiation, and more stable temperatures, could provide refugia where Martian life continues to exist, perhaps in forms adapted to conditions we are only beginning to imagine. The question of whether life on Mars would be related to life on Earth adds another layer of complexity to our investigation. The concept of panspermia, the idea that life might spread between planets through the exchange of material, suggests that Mars and Earth might share common biological origins. Rocks ejected from Mars by asteroid impacts have been found on Earth, and similarly, material from Earth has likely reached Mars. If hardy microorganisms could survive the journey through space, embedded within these rocks, then life on Mars and Earth might share common ancestors. Alternatively, life on Mars might represent an entirely independent genesis, a second origin of life within our solar system. Such a discovery would have profound implications for our understanding of how common life might be throughout the universe. If life arose independently on two planets within a single star system, it would suggest that the emergence of life is not an extraordinarily rare event, but perhaps an inevitable consequence of the right chemical and physical conditions. The search for past life on Mars has led to the identification of several particularly promising locations for future exploration. Jezero Crater, where the Perseverance rover is currently operating, was chosen because it contains clear evidence of an ancient river delta, an environment where organic materials would likely have been concentrated and preserved. The layered sediments in this crater hold the potential to preserve biosignatures from billions of years ago, when Mars had a thicker atmosphere and more abundant liquid water. Gale Crater, explored by the Curiosity rover, has revealed a complex history of environmental change, with evidence of both habitable and potentially hostile conditions occurring in cycles over geological time. The discovery of organic compounds in mudstones deposited in ancient lakes demonstrates that the chemical building blocks of life were present and could be preserved over vast periods of time. Other locations, such as the subsurface of Valles Marineris, the vast canyon system that stretches across much of the Martian equator, offer the possibility of accessing deep crustal materials that might harbor evidence of subsurface life. The polar regions, with their layered ice deposits and potential subsurface liquid water, represent another frontier for astrobiological exploration. The technological challenges of searching for life on Mars continue to push the boundaries of analytical chemistry and robotics. Current rovers carry sophisticated laboratories capable of analyzing samples at the molecular level, but they are still limited in their ability to definitively identify biosignatures. The planned Mars sample return mission represents a quantum leap in our investigative capabilities, as it will bring pristine Martian samples back to Earth for analysis with the most advanced instruments available to science. Future missions are being designed with increasingly sophisticated life detection capabilities. These might include DNA sequencers capable of identifying genetic material, if it exists in forms recognizable to terrestrial biology, or advanced mass spectrometers capable of detecting the subtle isotopic signatures that biological processes leave behind. Some proposed missions would target subsurface environments directly, using drilling capabilities to access the hidden realms where Martian life is most likely to persist. The philosophical implications of discovering life on Mars extend far beyond the scientific significance of such a finding. It would fundamentally alter our understanding of our place in the universe, transforming life from a unique phenomenon centered on Earth to a cosmic process that might be occurring throughout the galaxy. Such a discovery would raise profound questions about the nature of life itself, the conditions necessary for its emergence and evolution, and the possibility that intelligence might arise independently on multiple worlds. Even the discovery of past life on Mars, preserved as fossils in ancient rocks, would have transformative implications for biology and astrobiology. It would provide insights into alternative pathways of evolution, different solutions to the challenges of surviving in harsh environments, and potentially reveal whether the fundamental processes of life are universal or whether multiple forms of biology are possible. As we continue this gentle journey through the mysteries of Mars, it becomes clear that the red planet serves as far more than a simple target for scientific investigation. It represents a mirror for understanding our own world, a laboratory for testing our theories about life and planetary evolution, and a stepping stone toward understanding the broader cosmos. The patient work of rovers traversing its surface, orbiters mapping its features, and scientists analyzing its data continues to reveal a world of extraordinary complexity and enduring mystery. The search for life on Mars reminds us that the universe may be far more alive than we have previously imagined, filled with worlds where the ancient dance between chemistry and biology continues to unfold in ways we are only beginning to comprehend. Mars. The quiet world. As we continue our gentle voyage through the cosmos, we arrive at a world that has captured human imagination for millennia. Mars, that rust-colored beacon in our night sky, sits in patient solitude beyond Earth's orbit. Tonight, we'll drift alongside this ancient world and explore the countless mysteries it has revealed to us over decades of careful observation. Mars moves through space in its own unhurried rhythm, taking nearly 2 Earth years to complete a single orbit around our Sun. It's a world of subtle grandeur, where massive dust storms can engulf entire continents for months at a time, yet leave behind landscapes of haunting tranquility. The planet spins at almost the same rate as Earth, giving it days that feel familiar to us, lasting just 24 hours and 37 minutes. From our robotic ambassadors that have landed on its surface, we've learned that Mars is a world of profound silence. Without a thick atmosphere to carry sound waves very far, the Martian landscape exists in an almost meditative quiet. The thin air, composed mostly of carbon dioxide, creates a pressure so low that liquid water cannot exist stably on most of the surface. Yet this same tenuous atmosphere creates some of the most spectacular dust devils in the solar system, towering columns of swirling particles that dance across the plains like ghostly tornadoes. The surface of Mars tells a story written in stone and sediment across billions of years. Ancient river channels snake across continents, carved when the planet was young and its atmosphere was thicker. These dried riverbeds wind through landscapes that once knew the gentle flow of water, leaving behind intricate patterns that speak of a time when Mars may have been a very different world. Some of these channels are vast, dwarfing Earth's Grand Canyon, while others are delicate tributaries that branch like the veins of a leaf. Perhaps nowhere is Mars more mysterious than in its polar regions, where caps of frozen carbon dioxide and water ice advance and retreat with the changing seasons. During the Martian winter, these ice caps can extend nearly 1/3 of the way to the equator, only to sublimate back into the atmosphere as spring arrives. This seasonal breathing of the planet creates pressure changes that drive winds across the surface, redistributing dust and occasionally triggering the planet-wide storms that can last for months. The geology of Mars reveals a world that was once far more active than it appears today. Olympus Mons, the largest volcano in the solar system, rises nearly 21 kilometers above the surrounding plains. This massive shield volcano could have been built over hundreds of millions of years, with lava flows that created slopes so gentle you could walk up them without realizing you were climbing a mountain. The volcano's base is so wide that if you stood at its center, its edges would be hidden beyond the horizon. Scattered across the Martian surface are thousands of impact craters, each one a frozen moment from the violent early history of our solar system. Unlike Earth, where weather and geological activity have erased most ancient craters, Mars preserves these scars like a museum of cosmic collisions. Some craters are so large they create their own weather patterns, with winds swirling around their rims and dust settling in their floors in patterns that change with the seasons. In the northern hemisphere, vast plains stretch across landscapes that some scientists believe once held an ocean. These smooth expanses, broken only by scattered craters and the occasional mesa, may have been seafloors in an ancient Martian world where water was abundant. If this ocean existed, it would have been shallow and cold, perhaps freezing over for long periods, but it would have been an ocean nonetheless, lapping against shores that are now dry and silent. The southern highlands of Mars present a different character entirely, heavily cratered and ancient, representing some of the oldest terrain in the solar system. Here, the landscape is more rugged, with deep valleys and towering mesas that cast long shadows in the low-angled sunlight. Some of these formations contain minerals that could only have formed in the presence of water, suggesting that even in these ancient highlands, liquid water once flowed. Mars experiences seasons much like Earth does, thanks to the tilt of its axis. However, Martian seasons last nearly twice as long as Earth's, and the planet's elliptical orbit means that southern summer coincides with its closest approach to the Sun, making southern summers warmer and northern winters colder. This creates a subtle asymmetry in the planet's climate, with different patterns of dust storm activity and ice cap behavior in each hemisphere. The two small moons of Mars, Phobos and Deimos, are likely captured asteroids that orbit close to the planet. Phobos, the larger and closer of the two, races around Mars 3 times each Martian day, rising in the west and setting in the east. It's so close to the planet that it would appear about half the size of Earth's moon in the Martian sky. But its irregular, potato-like shape would make it look quite different from our familiar lunar sphere. What makes Mars particularly intriguing to scientists is the growing evidence that it may have harbored conditions suitable for life in its distant past. Certain types of clay minerals found on the surface could only have formed in neutral or slightly alkaline water, the kind that might have supported simple microorganisms. Some meteorites that originated from Mars and eventually fell to Earth contain organic compounds, though whether these are signs of past life or simply the result of non-biological chemistry remains a subject of intense study. The search for life on Mars continues through robotic explorers that drill into rocks, analyze soil samples, and search for organic compounds. These patient machines work in the thin sunlight and extreme cold, methodically examining their surroundings with instruments more sensitive than anything we could have imagined just decades ago. They found evidence of ancient hot springs, seasonal flows of briny water, and complex organic molecules preserved in billion-year-old rocks. Perhaps most remarkably, Mars occasionally releases small puffs of methane into its atmosphere. On Earth, most atmospheric methane is produced by living organisms, though it can also result from geological processes. The source of Martian methane remains unknown, but its presence suggests that somewhere beneath the surface, interesting chemistry is still taking place. Whether that chemistry involves life is one of the great questions driving our continued exploration of the red planet. As we drift alongside Mars in our imagination tonight, we can appreciate it not as a dead world, but as a planet still full of secrets. Its ancient surfaces preserve a record of the early solar system. Its seasonal changes demonstrate that planetary evolution continues even on seemingly inactive worlds. And its potential for past or even present life reminds us that the universe may be far more alive than we once thought. In the profound quiet of the Martian landscape, where dust devils dance across ancient lake beds and ice caps advance and retreat with the changing seasons, we find a world that challenges our understanding of what makes a planet habitable. The exploration of Mars, our enigmatic red neighbor, continues to unfold new chapters in humanity's understanding of planetary evolution and the tantalizing possibility of life beyond Earth. As we drift deeper into this cosmic narrative, we find ourselves contemplating not just what Mars was, but what it might yet become. The story of Mars is fundamentally a story of transformation. 4 billion years ago, this world bore little resemblance to the desolate landscape we observe today. Ancient riverbeds carved deep channels across continents. Vast lakes filled crater basins, their shorelines marked by sedimentary deposits that speak of countless seasons of evaporation and replenishment. The atmosphere, thick with carbon dioxide and water vapor, maintained pressures that allowed liquid water to flow freely across the surface. But Mars was smaller than Earth, and this seemingly minor detail would prove catastrophic over geological time. The planet's weaker gravitational field could not hold onto its atmospheric envelope as tenaciously as our homeworld. Solar wind, that constant stream of charged particles flowing from the sun, gradually stripped away the Martian atmosphere molecule by molecule. Without a strong magnetic field to deflect these cosmic winds, Mars found itself defenseless against this slow atmospheric hemorrhaging. As the atmosphere thinned, surface pressures dropped below the critical threshold needed for liquid water stability. The Great Lakes began to freeze and sublime directly into space. Rivers ceased their eternal flow, leaving behind only their fossilized channels as testament to a more hospitable past. The planet entered what we might call its long winter, a climatic shift from which it has never recovered. Yet Mars did not surrender all its secrets to the cold vacuum of space. Deep beneath the surface, protected from radiation and temperature extremes, water persists in vast underground reservoirs. Radar observations from orbiting spacecraft have revealed what appear to be substantial aquifers locked in the planet's subsurface, particularly around the polar regions. These hidden oceans may contain more water than exists in all of Earth's surface lakes and rivers combined. The implications of this subsurface water extend far beyond mere planetary inventory. Where liquid water exists, particularly in contact with rock formations that could provide chemical energy, the conditions for life become intriguingly possible. The deep subsurface of Mars may harbor ecosystems completely isolated from the surface world above, communities of microorganisms that have evolved in eternal darkness, sustained by chemical reactions rather than sunlight. Recent discoveries have added compelling evidence to this possibility. Methane detections in the Martian atmosphere, while sporadic and mysterious, suggest active geological or potentially biological processes occurring below ground. On Earth, a significant portion of atmospheric methane originates from biological sources. While geological processes can also produce methane, the seasonal variations and localized concentrations observed on Mars hint at something more dynamic than simple rock chemistry. The seasonal behavior of water on Mars continues to surprise researchers. As temperatures warm during Martian spring and summer, vast quantities of water vapor are released into the atmosphere, only to condense and freeze again as winter approaches. This annual cycle of sublimation and deposition creates dynamic patterns in the polar ice caps, with carbon dioxide ice advancing and retreating like glacial flows, revealing the underlying water ice beneath. These polar regions represent some of the most Earth-like environments on Mars. During summer months, temperatures can rise above freezing, creating conditions where liquid water might briefly exist on the surface. While such episodes would be fleeting, measured perhaps in hours rather than days, they demonstrate that Mars has not entirely abandoned the physical conditions necessary for liquid water. The planet's geological activity, while much reduced from its ancient past, has not ceased entirely. Seasonal dark streaks, called recurring slope lineae, appear on steep crater walls and canyon slopes during warm periods, possibly indicating the temporary flow of briny water. These features fade during colder seasons, suggesting a cyclical process tied to temperature variations. While their exact nature remains debated, they represent some of the strongest evidence for contemporary liquid water activity on Mars. Understanding Mars' atmospheric evolution provides crucial insights into planetary habitability more broadly. Venus, Earth, and Mars all began with similar initial conditions, yet evolved along dramatically different paths. Venus experienced a runaway greenhouse effect, while Mars lost its atmosphere to space. Only Earth maintained the delicate balance necessary for long-term surface water stability. This comparative planetology offers sobering lessons for understanding climate change on our own world. The mechanisms that stripped Mars of its atmosphere operate on Earth as well, though much more slowly due to our planet's stronger magnetic field and greater gravitational pull. Studying Mars' atmospheric loss helps scientists better understand the processes that could affect Earth's atmospheric stability over geological timescales. The search for past or present life on Mars has evolved from speculation to systematic scientific investigation. Each mission reveals new complexities in the planet's chemical inventory. Organic molecules, the carbon-based building blocks of life as we know it, have been detected in multiple locations. While these compounds can form through non-biological processes, their presence indicates that Mars possesses the chemical prerequisites for life. More intriguingly, some of these organic detections occur in association with minerals that form in the presence of water, suggesting that complex chemistry occurred in environments where life could potentially have thrived. The preservation of these molecules over billions of years demonstrates that Mars can serve as an archive of its own biological potential, with evidence of ancient life, possibly waiting in rocks yet to be examined. The planet's subsurface presents the most promising environment for discovering extant life. Protected from the harsh surface radiation, buffered against temperature extremes, and potentially supplied with liquid water and chemical energy sources, underground Mars may represent one of the most habitable environments in our solar system. Future missions are being designed specifically to drill deep enough to access these subsurface environments directly. As our exploration capabilities advance, Mars transforms from a distant object of curiosity into a world we might one day visit ourselves. The planet's gravity, while weaker than Earth's, is sufficient for human physiology. Its day length, approximately 24 hours and 37 minutes, closely matches our circadian rhythms. Raw materials for life support, including water, oxygen, and carbon, exist in abundance, though in forms that would require processing. The technological challenges of reaching Mars with human crews remain formidable, but they are no longer insurmountable. Journey times of 6 to 9 months, while lengthy, fall within the range of human endurance. The planet's seasonal cycles, while more extreme than Earth's, follow predictable patterns that could support long-term habitation strategies. Perhaps most significantly, Mars offers the possibility of backup location for human civilization. While Earth remains our only home for the foreseeable future, developing the capability to sustain human life on Mars provides insurance against existential risks that could threaten our species' survival. This motivation extends beyond mere exploration into the realm of long-term human survival strategy. The red planet continues to evolve, though at a pace measured in millions rather than thousands of years. Its polar ice caps advance and retreat, with orbital cycles lasting hundreds of thousands of years. Dust storms redistribute surface materials across continents. Impact events, while rare, continue to reshape the landscape and potentially deliver organic compounds from space. Climate models suggest that Mars may experience periodic warm periods when orbital mechanics align favorably. During these epochs, which occur every few million years, atmospheric pressure could rise sufficiently to allow liquid water stability over larger areas of the planet's surface. These windows of habitability may have provided opportunities for life to emerge, flourish, and potentially survive in subsurface refugia during intervening cold periods. The story of Mars serves as both cautionary tale and source of hope. It demonstrates how planetary environments can change dramatically over time, transforming from potentially habitable worlds into apparently barren landscapes. Yet it also suggests that life, once established, might find ways to persist even under seemingly impossible conditions. As you settle into sleep tonight, consider that Mars continues its ancient orbit around the Sun, its hidden waters flowing in darkness beneath a frozen surface, its atmospheric gases cycling with the seasons, its geological processes slowly reshaping the landscape. Somewhere in that cold world, in depths we have yet to explore, the question of life awaits an answer. The red planet holds its secrets patiently, as it has for billions of years, waiting for the next chapter in the story of exploration to unfold. In laboratories scattered across that distant world, chemistry continues its eternal experiments, perhaps nurturing forms of life that have learned to thrive in conditions we can barely imagine. Mars remains not just a destination for future exploration, but a mirror reflecting our own planet's precious and precarious position in the cosmic dance of habitability. As we reach the final chapter of our cosmic journey together, we find ourselves contemplating perhaps the most profound aspect of Mars and our relationship with the red planet, the question that has driven all human exploration and scientific inquiry since we first gazed upward at the rusty wanderer in our night sky. What does Mars tell us about ourselves, about life, and about our place in the vast cosmic dance we've been exploring throughout this gentle voyage through space and time? The story of Mars is ultimately a story of transformation, of worlds that change and evolve over billions of years. When we look at Mars today, with its thin atmosphere and frozen polar caps, its ancient riverbeds carved into stone, and its towering volcanoes silent for eons, we're seeing a planet that was once remarkably similar to our own Earth. 4 billion years ago, Mars likely had a thick atmosphere, flowing rivers, perhaps even oceans. It was a world where the conditions for life as we know it might have flourished in ways we can barely imagine. But Mars lost its magnetic field, that invisible shield that protects a planet's atmosphere from being stripped away by solar winds. Over millions of years, the Martian atmosphere grew thinner and thinner. The water that once flowed across its surface either escaped to space or froze into the ground. The planet that might once have been blue and green gradually transformed into the red desert world we observe today. This transformation offers us a humbling perspective on planetary evolution and the delicate balance required to maintain the conditions that make life possible. Yet even as Mars underwent this dramatic transformation, it preserved within its rocks and soil the chemical signatures of its more hospitable past. The rovers we've sent to Mars, those robotic explorers carrying our curiosity across millions of miles of space, have discovered evidence of ancient hydrothermal systems, of minerals that could only have formed in the presence of liquid water, of organic compounds that hint at the possibility that life might once have taken hold on the red planet. The seasonal changes we observe on Mars today, the dust storms that can engulf the entire planet, the sublimation and condensation of carbon dioxide at the polar caps, all remind us that Mars is not a dead world, but a dynamic one, still participating in the cosmic dance, even as it has been transformed by time. The planet's two small moons, Phobos and Deimos, continue their orbital ballet around Mars, though Phobos is gradually spiraling inward and will one day either crash into the planet or be torn apart by tidal forces to form a ring system around Mars. Our exploration of Mars represents one of humanity's greatest collaborative achievements. The spacecraft we've sent to Mars, from the early flyby missions to the sophisticated rovers currently exploring the surface, represent the combined efforts of thousands of scientists, engineers, and dreamers working together to extend our senses across the solar system. Each image transmitted back from Mars, each chemical analysis performed by a rover, each successful landing on the Martian surface represents a triumph of human curiosity and ingenuity. The search for life on Mars, whether ancient or present, continues to drive our exploration of the red planet. The possibility that life might have emerged independently on Mars would suggest that life is not unique to Earth, but might be a common feature of planetary evolution throughout the universe. The discovery of microbial life in Earth's most extreme environments, from deep ocean vents to the frozen valleys of Antarctica, has expanded our understanding of where life might be able to survive and has informed our search for similar environments on Mars. The subsurface of Mars, protected from the harsh radiation and extreme temperature variations of the surface, might harbour microbial communities that have persisted for billions of years. The seasonal variations in methane concentrations in the Martian atmosphere continue to intrigue scientists, as biological processes are one possible explanation for these fluctuations, though geological processes could also account for these observations. As we plan for future missions to Mars, including the eventual human exploration of the Red Planet, we're forced to confront profound questions about our responsibilities as explorers. How do we search for life on Mars without contaminating the planet with Earth life? How do we preserve the scientific integrity of Mars while also preparing for the possibility of human settlement? These questions require us to think not just as explorers, but as stewards of the cosmic environments we visit. The challenges of sending humans to Mars and sustaining them there for extended periods will require technological innovations that could benefit life on Earth as well. Closed-loop life support systems, techniques for extracting water and oxygen from the Martian environment, methods for growing food in extraterrestrial soils, all of these developments could have applications for sustainable living on our own planet. Mars also serves as a laboratory for understanding climate change and planetary atmospheres. By studying how Mars lost its atmosphere and transformed from a potentially habitable world to the desert planet we see today, we gain insights into atmospheric physics and planetary climate systems that help us better understand our own planet's climate. The dust storms, polar ice caps, and seasonal changes on Mars provide natural experiments in atmospheric dynamics that we can observe and study. G. Wells's War of the Worlds to Kim Stanley Robinson's Mars trilogy. These stories have helped us envision what human life on Mars might be like and have inspired generations of scientists and engineers to work toward making Mars exploration a reality. The relationship between science fiction and scientific exploration is particularly strong in Mars research, with each informing and inspiring the other. As we continue to explore Mars with increasingly sophisticated instruments and techniques, we're beginning to understand the planet not as a single, uniform world, but as a complex system with distinct geological provinces, each with its own history and characteristics. The northern lowlands and southern highlands tell different stories of planetary evolution. The Tharsis volcanic region, with its massive shield volcanoes, represents one of the largest volcanic systems in the solar system. Valles Marineris, the Grand Canyon of Mars, stretches for thousands of kilometers and reveals layers of Martian history in its exposed walls. The polar regions of Mars, with their layered ice caps and seasonal changes, provide records of Martian climate history, similar to how ice cores on Earth preserve records of our planet's past climates. The thin atmosphere of Mars, composed mostly of carbon dioxide, with traces of water vapor and other gases, continues to interact with the surface through dust storms, frost formation, and the seasonal exchange of gases between the atmosphere and polar ice caps. Recent discoveries of recurring slope lineae, dark streaks that appear and disappear seasonally on Martian slopes, suggest that liquid water might still occasionally flow on the Martian surface under very specific conditions. These observations remind us that Mars continues to surprise us, and that our understanding of the planet continues to evolve with each new mission and discovery. The technological achievements required for Mars exploration have pushed the boundaries of human engineering capabilities. Landing on Mars, with its thin atmosphere that provides some drag but not enough for simple parachute landings, requires innovative techniques like the sky crane system used to land the Curiosity and Perseverance rovers. Operating vehicles on Mars, with communication delays of up to 24 minutes each way, requires a level of autonomy and reliability that has advanced robotics and artificial intelligence technologies. As we look toward the future of Mars exploration, we envision sample return missions that will bring pieces of Mars back to Earth for detailed analysis in terrestrial laboratories. We plan increasingly sophisticated life detection experiments that will search for biosignatures in Martian rocks and soil. We prepare for the eventual human exploration of Mars, which will require international cooperation on a scale unprecedented in human history. The journey to Mars, whether robotic or human, represents more than just scientific exploration. It represents humanity's expansion beyond Earth, our first tentative steps toward becoming a multiplanetary species. The challenges of Mars exploration force us to work together, to pool our knowledge and resources, to think beyond national boundaries and toward our common future as citizens of the solar system. Mars teaches us about resilience and adaptation. Life on Earth has survived ice ages, asteroid impacts, and massive climate changes. If life ever existed on Mars, it might have found ways to persist even as the planet transformed around it. The possibility of life surviving in the Martian subsurface, protected from surface radiation and temperature extremes, reminds us of life's remarkable ability to adapt to changing conditions. The study of Mars also teaches us about the preciousness of our own planet, Earth's thick atmosphere, strong magnetic field, and perfect distance from the Sun create conditions that have allowed life to flourish for billions of years. The transformation of Mars from a potentially habitable world to a cold desert reminds us that planetary habitability is not guaranteed, and that the conditions that make Earth special require our protection and stewardship. As we continue our exploration of Mars, we're reminded that we're participating in one of the greatest adventures in human history. Every image from Mars, every chemical analysis, every successful landing represents a triumph of human curiosity and determination. We're living through the era when humanity first began to explore other worlds in detail, to search for life beyond Earth, to expand our presence into the solar system. The red planet, that wandering star that has captured human attention for millennia, continues to reveal its secrets to us. Each mission brings new discoveries, new questions, and new possibilities. Mars reminds us that the universe is full of worlds waiting to be explored, mysteries waiting to be solved, and wonders waiting to be discovered. Tonight, as you settle into sleep, perhaps you can imagine yourself standing on the Martian surface, looking up at the butterscotch sky and the two small moons racing across the heavens. Perhaps you can envision the ancient rivers that once flowed across the Martian landscape, the possible life forms that might once have called Mars home, or the future human explorers who will walk the red planet's surface and continue the great work of exploration and discovery. Mars teaches us that we are part of something larger than ourselves, participants in a cosmic story that spans billions of years and countless worlds. The same forces that shaped Mars also shaped Earth. The same elements that make up Martian rocks also flow through our veins, and the same curiosity that drives us to explore Mars also connects us to every human who has ever looked up at the night sky and wondered what lies beyond. In our exploration of Mars, we discover not just the secrets of another world, but something about ourselves, about our capacity for wonder, our drive to explore, and our ability to work together to achieve seemingly impossible goals. Mars is more than just our planetary neighbour. It's a mirror that reflects our own world's precious nature, a laboratory for understanding planetary evolution, and a destination that represents humanity's first steps toward the stars. Now starts the stage 2. How will Mars look in the future? I hope you are still awake and listening. This journey is going to be very exciting. Looking at the landscape of Mars and contemplating its future transformation, we journey into one of the most fascinating chapters of human ambition and planetary science. The red planet, that rust-coloured wanderer in our night sky, may not remain red forever. In fact, if we peer far enough into the future, Mars might become something entirely different, something that would challenge our very understanding of what it means to transform a world. Picture Mars as it exists today, a cold and desolate sphere spinning through the cosmic darkness. The average temperature hovers around -80 degrees Fahrenheit, cold enough to freeze carbon dioxide from the atmosphere into polar ice caps that grow and shrink with the Martian seasons. The atmosphere is thin, composed mostly of carbon dioxide, with traces of nitrogen and argon, creating a surface pressure barely 1% of what we experience here on Earth. If you were to stand on Mars today without a pressure suit, your blood would literally boil from the low atmospheric pressure, while the lack of a substantial magnetic field means that deadly radiation from space bombards the surface with ruthless persistence. Yet this harsh reality hasn't stopped humanity from dreaming of a different Mars, a Mars transformed through human ingenuity and patience into something resembling the garden worlds of science fiction. The concept of terraforming, literally meaning earth-shaping, has captured imaginations for decades, representing perhaps the ultimate expression of human technological ambition. It's the idea that we might one day possess the tools and knowledge necessary to reshape entire planets, to take the frozen wastes of Mars and gradually, over centuries or millennia, transform them into a world where Earth life could flourish under open skies. The story of how Mars might look in the future begins with understanding how it became the world we observe today. Billions of years ago, Mars was a very different place. Evidence suggests that ancient Mars possessed a thicker atmosphere, flowing rivers, and possibly even oceans. The planet's surface bears the scars of this watery past in the form of dried riverbeds, mineral deposits that could only have formed in the presence of liquid water, and what appear to be ancient shorelines marking the boundaries of long-vanished seas. What happened to this ancient, potentially habitable Mars provides crucial insights into what might be possible for its future. The planet's smaller size meant that its core cooled more rapidly than Earth's, causing it to lose the magnetic field that once protected its atmosphere from the solar wind. Over millions of years, this stellar breeze gradually stripped away much of Mars' atmospheric envelope, allowing the remaining water to escape into space or freeze into the polar ice caps and underground permafrost deposits. Understanding this process of atmospheric loss is fundamental to any serious discussion of Martian terraforming, because it reveals both the challenges and the possibilities that await future planetary engineers. The first step in transforming Mars would likely involve addressing its atmospheric deficiency. Various proposals have emerged over the decades, each with its own merits and complications. One approach involves releasing greenhouse gases into the Martian atmosphere to create a runaway greenhouse effect that would gradually warm the planet and thicken its atmospheric envelope. Carbon dioxide trapped in the polar ice caps and in the planet's soil could be liberated through carefully controlled heating, while more potent greenhouse gases like methane or engineered compounds could amplify the warming effect. Another approach focuses on melting the water ice locked away in Mars' polar regions and underground permafrost. If this water could be converted to vapor and released into the atmosphere, it would not only increase atmospheric pressure, but also provide the raw material for weather systems that could help distribute heat around the planet. The process would be gradual, taking place over centuries, but the end result could be a Mars with a much more substantial atmosphere and significantly higher surface temperatures. The introduction of extremophile organisms represents another potential pathway for Martian transformation. Certain microorganisms found in Earth's most hostile environments, from the depths of Antarctic ice to the acidic hot springs of Yellowstone, demonstrate life's remarkable ability to survive and even thrive in conditions that would be lethal to most other organisms. If such organisms could be adapted to Martian conditions, they might serve as the foundation for a gradually expanding biosphere that could begin the long process of transforming the planet's atmosphere and surface chemistry. Imagine Mars several centuries into such a transformation process. The polar ice caps, once permanent fixtures of the Martian landscape, might have partially melted, releasing vast quantities of water vapor and carbon dioxide into the atmosphere. The sky, once a butterscotch yellow due to suspended dust particles, might gradually shift toward a more familiar blue as the atmosphere thickens and water vapor begins to condense into clouds. These clouds would represent the first Martian weather systems in billions of years, creating cycles of precipitation that could begin to fill the ancient riverbeds and lake basins that currently lie dry and empty. The surface temperature would rise gradually, perhaps reaching levels that would allow liquid water to exist stably on the surface for the first time in geological ages. This would mark a crucial threshold in the transformation process, as liquid water is essential for the complex chemistry that underlies all known forms of life. Areas that are currently frozen wastelands might begin to show signs of seasonal melting, creating temporary streams and ponds that could serve as habitats for specially adapted organisms. As the atmosphere continues to thicken, atmospheric pressure would gradually increase, reducing the radiation exposure that currently makes the Martian surface so hostile to life. The planet might develop its own modest ozone layer, providing additional protection from harmful ultraviolet radiation. Wind patterns would change as the atmosphere becomes more substantial, potentially reducing the massive dust storms that currently can engulf the entire planet for months at a time. The timeline for such transformations remains a subject of considerable debate among scientists and engineers. Conservative estimates suggest that meaningful atmospheric changes might take thousands of years to achieve, while more optimistic projections propose that significant progress could be made within centuries. Much depends on the specific methods employed and the scale of human commitment to such an undertaking. The technological challenges are immense, requiring advances in fields ranging from atmospheric engineering to synthetic biology, from space-based manufacturing to planetary-scale climate modeling. One of the most intriguing aspects of Martian terraforming is how it might proceed in stages, with each phase building upon the successes of the previous one. The earlier stages would likely focus on establishing sustainable human settlements that could serve as bases for larger-scale transformation efforts. These settlements would need to be largely self-sufficient, capable of producing their own food, water, and building materials from local Martian resources. As these settlements grow and multiply, they might begin to create localized microclimates around their installations. Greenhouse complexes could expand beyond their original boundaries, creating pockets of Earth-like conditions that could gradually spread across larger areas. The waste heat from industrial processes could be used to warm surrounding areas, while carefully managed atmospheric releases could begin the process of thickening the local atmosphere. Over time, these localized transformation efforts might begin to merge and interact, creating regional changes that could eventually influence planetary-scale systems. Areas around major settlements might develop their own weather patterns, with increased humidity and cloud formation creating positive feedback loops that accelerate the warming process. The success of these regional transformations could provide both the technology and the confidence needed to attempt more ambitious planetary-scale interventions. The question of what life might look like on a partially terraformed Mars opens up fascinating possibilities. The first organisms to thrive in the changing environment would likely be extremophils, bacteria, and archaea that could tolerate the still harsh conditions while beginning the process of biological transformation. These microorganisms could gradually alter the soil chemistry, breaking down toxic compounds and beginning to create the complex organic matter that forms the foundation of more complex ecosystems. As conditions continue to improve, more complex organisms might be introduced or might evolve from the initial microbial populations. Hardy plants adapted to low oxygen, high radiation environments could begin to colonize areas around human settlements, their photosynthesis contributing additional oxygen to the atmosphere, while their root systems help to stabilize soil and create habitats for other organisms. The introduction of more complex life forms would need to be carefully managed to avoid ecological disasters that could derail the entire terraforming process. Each new species would need to be thoroughly tested to ensure that it could survive in Martian conditions without causing unintended consequences for the developing ecosystem. The goal would be to create a stable, self-sustaining biosphere that could continue to evolve and expand even without constant human intervention. Looking further into the future, a successfully terraformed Mars might bear little resemblance to the planet we know today. Instead of the rust-colored desert that currently dominates the Martian landscape, vast areas might be covered with vegetation, specially adapted to the unique conditions of the transformed planet. These plants might not look exactly like their Earth counterparts, having evolved or been engineered to thrive in the lower gravity, different atmospheric composition, and altered seasonal patterns that would characterize the new Mars. Bodies of water might once again flow across the Martian surface, filling the ancient impact craters and flowing through valleys carved by rivers that dried up billions of years ago. These new Martian seas and rivers would likely have different chemical compositions than Earth's waters, reflecting the unique mineral content of Martian soil and the different atmospheric conditions. They might support ecosystems unlike anything found on Earth, with organisms that have adapted to the specific challenges and opportunities presented by the Martian environment. The sky above this transformed Mars might display colours and phenomena unknown on Earth. The different atmospheric composition and lower gravity could create unique cloud formations and weather patterns. Sunsets might paint the sky in hues of green and purple rather than the familiar reds and oranges of Earth, while the presence of two small moons could create complex tidal patterns in any bodies of water that form. Human settlements on this transformed Mars would likely be vastly different from the enclosed habitats that characterize current proposals for Martian colonization. With a breathable atmosphere and liquid water readily available, humans might be able to live in open cities, their buildings designed to take advantage of the unique aesthetic and functional possibilities offered by the Martian environment. Architecture might evolve to accommodate the lower gravity, with buildings that could never stand on Earth due to their height and delicate construction. The social and cultural implications of living on a terraformed Mars would be profound. The inhabitants of such a world would likely develop their own distinct identity, shaped by the unique challenges and opportunities of their environment. Their relationship with the planet would be fundamentally different from humanity's relationship with Earth, based as it would be on the conscious decision to transform an entire world, rather than simply adapting to existing conditions. Yet even as we contemplate such transformations, it's important to remember that Mars would retain many of its fundamental characteristics. The planet's smaller size means that gravity would remain about 38% of Earth's, creating permanent differences in how both humans and other organisms would develop and function. The greater distance from the Sun means that solar energy would be less abundant, potentially requiring different strategies for powering both human civilization and natural ecosystems. The Martian day, at 24 hours and 37 minutes, is remarkably similar to Earth's, but the Martian year is nearly twice as long, creating seasonal patterns unlike anything experienced on our home planet. These extended seasons would profoundly influence both the climate and the ecology of a terraformed Mars, creating opportunities for seasonal migrations and adaptations that could produce ecosystems of remarkable complexity and beauty. As we drift deeper into these possibilities, we might imagine ourselves standing on the surface of this transformed Mars centuries or millennia from now. The air, while still different from Earth's, might be breathable without artificial assistance. The horizon might shimmer with the movement of distant weather systems, while overhead, clouds drift across a sky that has returned to blue after billions of years of yellow desolation. The ground beneath our feet might be covered with vegetation that rustles in the Martian breeze, plants that represent the successful marriage of Earth biology with Martian conditions. In the distance, we might see the glint of sunlight on water, marking the location of a lake or river that exists for the first time since the planet's ancient past. This vision of Mars represents more than just a scientific possibility. It embodies humanity's deepest aspirations for growth, exploration, and the expansion of life throughout the cosmos. Whether such transformations will ever prove practical or desirable remains an open question, but the very possibility speaks to the remarkable potential that lies dormant within both human ingenuity and the planets that surround us. The story of Mars's future transformation reminds us that worlds are not permanent, unchanging fixtures in the cosmic landscape. They are dynamic systems that can evolve, be transformed, and potentially be reborn. As we continue to explore Mars through robotic missions and prepare for the first human expeditions to the Red Planet, we carry with us not just scientific instruments and survival equipment, but also dreams of what Mars might one day become. In contemplating these possibilities, we find ourselves at the intersection of science and imagination, where rigorous research meets the boundless creativity of human vision. The Mars of the future, whether transformed by human effort or left to evolve according to natural processes, will undoubtedly surprise us in ways we cannot yet anticipate. Now, as we venture deeper into this Martian reverie, let us pause and consider the delicate dance between atmosphere and surface that will shape this transformed world. You see, the Mars of tomorrow won't simply be Earth painted red. It will be something entirely new, a hybrid realm where familiar processes unfold under alien conditions, creating landscapes and phenomena that exist nowhere else in our solar system. The atmospheric transformation we've begun to envision will unfold with a patience that mirrors geological time itself. As those carefully engineered microbes continue their ancient alchemy, converting carbon dioxide to oxygen molecule by precious molecule, the very character of Martian weather will begin to shift. The first changes will be subtle, almost imperceptible to any hypothetical observer standing on that russet plain. Perhaps a slight thickening of the air, a barely noticeable change in how dust settles after the great storms that still sweep across the planet's face. But patience, dear listener, for even these modest beginnings will cascade into transformations beyond our current imagination. As the atmosphere grows denser, it will begin to hold heat more effectively, creating the first tentative greenhouse effect. The temperature swings that currently plague Mars, those brutal transitions from day to night that can span hundreds of degrees, will begin to moderate. The atmosphere will become a blanket, gentle and warming, allowing liquid water to exist not just in fleeting moments, but in stable pools, streams, and eventually vast bodies that might one day rival Earth's own lakes and seas. Picture, if you will, the first Martian clouds forming in this thickening atmosphere. They won't be the familiar white puffs of Earth, but something uniquely Martian, tinged perhaps with the fine dust that gives the planet its characteristic hue. These clouds will cast shadows across the landscape, creating patterns of light and dark that dance across ancient impact craters and towering volcanic peaks. The interplay of shadow and rust-colored terrain will create a visual symphony unlike anything in our terrestrial experience. As decades turn to centuries, and centuries to millennia, the water cycle will establish itself with increasing confidence. The polar ice caps, those frozen repositories of Mars's watery past, will begin to contribute more generously to this emerging cycle. Water vapor will rise into the atmosphere, condense in those distinctive Martian clouds, and fall as precipitation. But this won't be Earth's gentle rain. Martian precipitation will have its own character, shaped by the planet's lower gravity and unique atmospheric composition. Imagine the first Martian snow falling on those ancient highlands, each flake drifting downward in the gentle gravity, taking longer to settle than its earthly counterparts. The snow will accumulate differently too, creating drifts and patterns that follow Martian physics, building up in ways that would seem impossible on Earth. When spring arrives in the Martian year, which lasts nearly twice as long as our own. This snow will melt into streams that carve new channels through landscapes that have remained unchanged for billions of years. The emerging hydrological cycle will breathe life into Mars's geological processes in ways that have been dormant since the planet's youth. Erosion will resume its patient work, but it will sculpt the landscape according to Martian rules. Rivers will flow more slowly in the reduced gravity, meandering in broader curves, creating floodplains and deltas that follow different mathematical principles than those on Earth. These waterways will carry sediments in new patterns, depositing them to form rock layers that future Martian geologists might study to understand this great transformation. But water alone cannot complete this metamorphosis. The soil itself must undergo its own renaissance. For billions of years, Martian soil has been essentially sterile, bathed in radiation and scoured by chemical processes that make it hostile to life as we know it. The transformation of this regolith into something that can support living ecosystems represents one of the most profound challenges in our Martian terraforming vision. The engineered organisms we've introduced will play a crucial role here, but they won't work alone. As the atmosphere thickens and the radiation environment improves, we might introduce more complex microorganisms, each designed for specific tasks in this grand biological engineering project. Some might specialize in breaking down the toxic perchlorates that currently poison Martian soil. Others might focus on creating the complex organic compounds that form the foundation of fertile soil. Still others might establish the crucial nitrogen cycle, converting atmospheric nitrogen into forms that plants can use. This biological transformation of the soil will happen gradually, spreading outward from carefully chosen locations like ripples in a pond. We might begin in the deepest valleys, where the atmosphere will be thickest and the conditions most favorable. From these protected nurseries, life will slowly colonize higher elevations, adapting and evolving as it encounters the unique challenges of the Martian environment. As this process unfolds over countless generations, we'll witness the emergence of something unprecedented in the solar system, a genuinely hybrid biosphere. The organisms that eventually populate this transformed Mars won't be simple transplants from Earth. They'll be evolved for Martian conditions, shaped by the planet's unique combination of lower gravity, longer seasons, different atmospheric composition, and alien soil chemistry. Consider the plants that might eventually clothe the Martian landscape. They'll need to be fundamentally different from their terrestrial ancestors. In the lower gravity, they might grow taller and more delicate than Earth plants, reaching skyward in ways that would be impossible under our planet's stronger gravitational pull. Their leaves might be adapted to make the most of the different quality of sunlight that filters through Mars's thinner atmosphere, perhaps taking on colours and configurations that would seem alien to earthly eyes. The seasonal rhythms of these Martian ecosystems will follow the planet's own unique calendar. A Martian year lasts 687 Earth days, meaning that seasons extend for months longer than we're accustomed to. Plants and animals adapted to this rhythm will have growth cycles, reproductive patterns, and behavioural adaptations that reflect these extended seasons. Spring on Mars might see explosive growth as organisms race to take advantage of the warming temperatures and increasing daylight. Summer could be a time of deep dormancy in some regions, as organisms conserve resources through the extended warm period. But perhaps most fascinating of all will be the unique weather phenomena that emerge from this transformed Martian atmosphere. The planet's lower gravity will allow atmospheric phenomena to reach scales impossible on Earth. Thunderstorms might tower to heights of 50 kilometers or more, creating lightning displays that dwarf anything in our terrestrial experience. The interplay between the planet's still active dust storm systems and the new water-based weather will create meteorological spectacles that exist nowhere else in the solar system. The dust storms themselves will gradually change character as the atmosphere thickens and water becomes more prevalent. Rather than the planet-encompassing dust storms that currently rage for months at a time, we might see more localized but more intense weather systems. These storms will still carry the distinctive red dust that gives Mars its character, but they'll be tempered by humidity and precipitation in ways that create entirely new types of weather patterns. As we drift deeper into this vision of Mars transformed, we begin to see a world that, while still recognizably alien, has become genuinely habitable. The thin, poisonous atmosphere of today has given way to something breathable, if still exotic. The sterile, radiation-scoured surface has become a complex ecosystem supporting countless forms of life. The frozen, desiccated landscape has awakened to the sound of flowing water and the whisper of wind through vegetation. Yet even in this transformed state, Mars will retain its essential Martian character. The red dust will still color the sky in its distinctive salmon hues during certain weather conditions. The two small moons, Phobos and Deimos, will still race across the sky in their peculiar orbits, creating eclipse patterns and tidal effects unlike anything experienced on Earth. The great volcanic mountains, Olympus Mons and the Tharsis volcanoes, will still dominate their regions, though they may now be clothed in clouds and perhaps even snow. The day-night cycle will remain distinctly Martian, just 40 minutes longer than Earth's day, creating subtle but persistent rhythms that shape all life on the planet. The seasons will still follow their extended pattern, nearly twice as long as Earth's, creating annual cycles of growth, reproduction, and dormancy that span what we would consider multiple Earth seasons. This is the Mars of our imagination, a world transformed, yet still alien, familiar, yet utterly unique. It represents perhaps the greatest engineering project in human history, a centuries-long effort to awaken a sleeping planet and give it new life. The transformation of Mars, engineering a new world. As we continue our cosmic journey, we find ourselves contemplating one of humanity's most audacious dreams, the transformation of Mars from a desolate, rust-colored wasteland into a living, breathing world. This process, known as terraforming, represents perhaps the ultimate expression of planetary engineering, a slow dance between technology and time that could unfold over centuries or even millennia. The challenge before us is immense, almost incomprehensible in its scope. Mars today exists as a frozen desert, its thin atmosphere composed mostly of carbon dioxide, with surface pressures less than 1% of Earth's. The average temperature hovers around -67 degrees Celsius, cold enough to freeze carbon dioxide into dry ice at the polar caps. Without a substantial magnetic field to protect it, the planet is bombarded by cosmic radiation that would prove lethal to most Earth life. The soil contains toxic perchlorates, chemical compounds that would poison most terrestrial organisms. Yet within this harsh reality lies the raw material for transformation. The first whispers of change would likely begin with the atmosphere itself. Scientists envision releasing greenhouse gases into the Martian sky, compounds far more potent than carbon dioxide in their ability to trap heat. Perfluorocarbons, for instance, could warm the planet's surface while remaining stable in the thin atmosphere for thousands of years. As temperatures slowly rise, degree by precious degree, the polar ice caps would begin their ancient retreat. Water vapor would join the atmospheric dance, creating the first tentative clouds to grace Martian skies in billions of years. This atmospheric thickening would trigger cascading changes across the planet's surface. The increased pressure would allow liquid water to exist in stable pools and streams, no longer instantly boiling away into the vacuum-thin air. The first Martian rains in geological ages would begin to fall, initially as brief, scattered showers, but gradually developing into more sustained precipitation patterns. These early weather systems would be alien to Earth-born eyes, shaped by Mars's unique geography and the planet's longer seasons, each lasting roughly twice as long as Earth's due to Mars's more distant orbit around the Sun. As the atmosphere continues to thicken and warm, we would witness the gradual awakening of Mars's hydrological cycle. Ancient riverbeds, carved billions of years ago when Mars was young and warm, would flow with water once again. The vast canyon system of Valles Marineris might partially flood, creating a series of interconnected lakes stretching across thousands of kilometers. The northern lowlands, which some scientists believe once held an ocean, could see the return of standing water bodies, though these new Martian seas would be unlike anything on Earth, their chemistry and behavior shaped by the planet's unique conditions. The introduction of life into this transforming world would require careful orchestration. The first colonists would likely be microorganisms, hardy extremophiles engineered to thrive in the still harsh Martian environment. These microscopic pioneers would begin the slow work of soil remediation, breaking down toxic compounds and gradually building up organic matter in the regolith. Cyanobacteria, those ancient architects of Earth's own atmospheric transformation, might be modified to function in the Martian environment, slowly adding oxygen to the atmosphere through photosynthesis. Plant life would follow, beginning with the hardier species adapted to Mars's unique challenges. The lower gravity, about 38% of Earth's, would allow plants to grow in ways impossible on our home world. Trees might reach extraordinary heights, their structures able to support more mass with less gravitational stress. Root systems could develop differently, spreading through the less dense soil in patterns shaped by the planet's distinct geology. The reduced gravity would influence every aspect of life on the transformed Mars. Water would behave differently, flowing in streams and rivers that would seem almost ethereal to Earthborn observers. Rain would fall more gently, each droplet taking longer to reach the ground. The atmosphere, even when thickened, would likely remain less dense than Earth's, creating weather patterns and wind systems unlike anything we know. Dust storms, Mars's signature atmospheric phenomenon, would continue to occur, though perhaps less violently, as the denser atmosphere provides more resistance to wind-driven particles. Animal life, when eventually introduced, would need to be carefully selected and possibly genetically modified to thrive in the Martian environment. The lower gravity would allow for entirely new forms of locomotion and body structure. Birds might develop wingspans impossible on Earth, while land animals could achieve sizes and proportions constrained by terrestrial gravity. The longer day-night cycle, with each Martian day lasting about 24 hours and 37 minutes, would influence biological rhythms and behaviors in ways we can only begin to imagine. The color palette of this new world would gradually shift from the monochromatic rust and ochre of modern Mars to something richer and more varied. Green would creep across the landscape as plant life takes hold, but it would be a distinctly Martian green, adapted to the planet's different light conditions and atmospheric composition. The sky, currently a butterscotch hue due to suspended dust particles, might gradually shift toward blue as the atmosphere thickens and water vapor increases, though it would likely retain a unique tint that would forever mark it as alien. Seasonal changes on Mars would be dramatic and extended, each lasting roughly twice as long as Earth's seasons, due to the planet's more elliptical orbit and greater distance from the Sun. Spring would bring massive melting events as polar ice caps retreat, feeding rivers and lakes across the planet. Summer in the southern hemisphere would be particularly intense as Mars reaches its closest approach to the Sun during this period, creating weather patterns and temperature variations unknown on Earth. The transformation would not be uniform across the planet's surface. Mars's dramatic topography, including the largest volcano in the solar system and canyon systems that dwarf the Grand Canyon, would create diverse microclimates and ecosystems. The slopes of Olympus Mons might support entirely different communities of life than the depths of Valles Marineris, or the rolling plains of the northern lowlands. As centuries pass and the transformation deepens, we might see the emergence of genuinely Martian ecosystems, Communities of life adapted not just to survive on Mars, but to thrive there. These would be alien ecologies, operating under different rules than Earth's biosphere, shaped by lower gravity, different atmospheric composition, extended seasons, and unique geological features. The presence of Mars's two small moons, Phobos and Deimos, would add another layer of uniqueness to this transformed world. These rocky satellites, much smaller than Earth's moon, would race across the Martian sky, with Phobos completing an orbit in just over 7 hours. Their gravitational influence on the planet's new oceans and atmosphere would create tidal patterns and atmospheric oscillations completely foreign to Earth-born experience. This grand transformation would represent more than just an engineering achievement. It would mark humanity's first successful creation of a second biosphere, a backup for Earth's precious cargo of life. The techniques developed and lessons learned in terraforming Mars would provide invaluable knowledge for future planetary engineering projects, perhaps on Venus or the moons of the outer solar system. The timescales involved in such a transformation humble human perception. What we might accomplish in a human lifetime would represent merely the first tentative steps in a process that could span dozens of generations. Children born on the early Mars might live to see the first permanent lakes. Their grandchildren might witness the first forests. Their great-great-grandchildren might breathe the first truly breathable Martian air. Yet even as we dream of this transformed Mars, we must remember that it would remain fundamentally alien, a world shaped by its own unique history and physical properties. The lower gravity would create landscapes impossible on Earth. The different atmospheric composition would support weather patterns we have never seen. The longer days and extended seasons would drive biological rhythms unknown to terrestrial life. This Mars of the future would be neither Earth nor the Mars we know today, but something entirely new, a hybrid world, part natural evolution and part conscious design, where the red planet's ancient geology meets humanity's technological ambition. It would be a world where rust-colored dust devils still dance across ancient impact craters, but where green valleys now wind between them. Where the morning sky might show a blue-green hue unknown on either Earth or present-day Mars, and where two small moons continue their eternal race across heavens that now echo with the calls of birds and the whisper of wind through leaves. In this vision of Mars transformed, we see not just the power of technology and human determination, but the profound adaptability of life itself. Given time, patience, and careful nurturing, even the most desolate worlds might bloom with the complexity and beauty that we associate with our own precious Earth. The transformation of Mars continues its patient march through deep time, guided by the same gentle forces that have shaped worlds for billions of years. As we drift deeper into this cosmic reverie, let us imagine the slow choreography of atmospheric change unfolding across the red planet like a whispered symphony played in geological time. Picture the Martian atmosphere growing denser, breath by breath, century by century. The engineered greenhouse gases we've released work their quiet magic, trapping solar radiation and slowly warming the frozen ground beneath. This is not the violent terraforming of science fiction, but something far more elegant, a gradual awakening that mirrors the way dawn creeps across a sleeping landscape. The polar ice caps begin their ancient dance of sublimation and condensation. Water vapor rises from the southern cap like invisible prayers, joining the thickening atmosphere in a delicate ballet of molecular exchange. The atmospheric pressure creeps upward millimeter by mercury millimeter, creating conditions where liquid water can exist without immediately boiling away into the thin air. Beneath the surface, permafrost layers that have slumbered for eons begin their slow thaw. The ground ice, locked away since Mars lost its original atmosphere billions of years ago, releases its ancient moisture into the warming world above. This water carries with it minerals and nutrients, the dissolved essence of Martian geology, creating the first primitive soils where life might take root. The introduced extremophile organisms work their microscopic miracles in this transformed environment. Methanogenic archaea deep in the subsurface produce methane as they consume the organic compounds we've delivered. This methane rises through the soil and rock, adding its own contribution to the greenhouse effect in a beautiful example of biological feedback. The planet begins to warm itself, life calling to life across the vast Martian landscape. As temperatures rise and atmospheric pressure increases, something remarkable begins to happen. The first temporary pools of liquid water appear in the deepest basins and craters. These ephemeral lakes exist for only hours or days before evaporating, but their very existence marks a threshold crossed, a promise of the watery world Mars might become. The cyanobacteria we've seeded in these fleeting pools work their ancient alchemy, splitting water molecules and releasing oxygen into the atmosphere. It's the same process that transformed Earth's atmosphere billions of years ago, now playing out again on a different world under alien skies. The oxygen concentration remains vanishingly small at first, measured in parts per million, but it represents the first stirrings of an atmosphere that might one day support complex life. Weather patterns begin to emerge from this atmospheric awakening. The thicker air can hold more heat, creating temperature gradients that drive wind systems across the planet. Dust storms still rage across the Martian surface, but now they're accompanied by something new, the first tentative clouds of water vapor condensing in the cold upper atmosphere. These clouds cast shadows on the warming ground below, creating the planet's first weather in the modern sense. Rain doesn't fall yet. The atmospheric conditions aren't quite right for that miracle. But ice crystals form and sublime, adding their moisture to the slowly cycling water budget of the transforming world. The great volcanoes of Mars, Olympus Mons, and the Tharsis Shield Complex stand like sleeping giants in this changing landscape. Deep beneath their massive bulk, geological processes continue their patient work. The added atmospheric pressure and changing thermal conditions might even trigger new volcanic activity, releasing additional gases and minerals to fuel the transformation. As decades pass into centuries, the changes become more pronounced. The atmospheric pressure reaches levels where humans might walk the surface with only breathing apparatus, no longer requiring full pressure suits. The temperature swings moderate as the thicker atmosphere stores and redistributes heat more efficiently. The deadly radiation from space, once a constant threat, becomes partially filtered by the growing atmospheric shield. Plant life begins its tentative colonization of this new world. Hardy mosses and lichens, genetically modified to thrive in the unique Martian conditions, spread across the regolith in slow green waves. These pioneer species work to break down rock and create the first true soils, their roots penetrating deep into the ancient Martian substrate. The low gravity affects everything about how life develops on Mars. Plants grow taller and more delicate than their Earth counterparts, their stems and leaves adapted to the gentle pull that is only 38% of what we know. Trees, when they eventually appear, reach impossible heights by Earth standards, their trunks slender and graceful as they stretch toward the butterscotch sky. Water begins to flow more regularly across the Martian surface. The first streams appear in the deepest valleys, fed by melting ground ice and the growing water cycle. These waterways carve new channels in the ancient landscape, adding their fresh scars to the fossil riverbeds that speak of Mars' distant past. Lakes form in the lowest basins, their waters rich with dissolved minerals from the Martian soil. These bodies of water become oases for life, supporting communities of microorganisms that slowly diversify and evolve. The salinity varies widely, some lakes fresh enough to drink, Others concentrated brines that support only the most specialized extremophiles. The seasonal cycles of Mars, driven by its tilted axis and elliptical orbit, create unique patterns of growth and dormancy. The Martian year, nearly twice as long as Earth's, allows for extended growing seasons, followed by long periods of winter dormancy. Life adapts to these rhythms, developing strategies for surviving the extended cold periods when sunlight is scarce and temperatures plummet. As the centuries accumulate, more complex ecosystems begin to emerge. Insects, specially adapted for the low pressure and unique atmospheric composition, appear in the warming world. They pollinate the expanding plant communities and serve as food for the first vertebrates, small creatures that breathe the thin but increasingly oxygen-rich air. The magnetic field remains weak, but the thickening atmosphere provides increasing protection from cosmic radiation. Life develops its own protective strategies, producing compounds that shield against harmful radiation, creating communities in sheltered valleys and caves, adapting in countless ways to the unique challenges of the Martian environment. Human settlements expand during this time, no longer isolated outposts, but thriving communities that work in partnership with the transforming ecosystem. The colonists develop new agricultural techniques suited to the low gravity and unique soil conditions. They harvest the products of the changing world, from the minerals concentrated in the evaporating lakes to the organic compounds produced by the expanding biosphere. The atmosphere continues its slow thickening, approaching levels where simple masks might suffice for human respiration. The oxygen content, while still far below Earth levels, supports increasingly complex life forms. The first forests appear in the most favorable locations, their canopies creating microclimates that support even more diverse communities of life. Weather systems become more complex as the atmosphere thickens. The first true rain falls on Mars in eons, though it's unlike Earth rain, adapted to the lower pressure and different atmospheric composition. These precipitation events trigger explosive growth in the plant communities, creating seasonal blooms that paint the Martian landscape in unexpected colors. The polar ice caps stabilize in their new configuration, serving as vast reservoirs that regulate the planet's water cycle. Seasonal melting feeds the growing river systems, while winter freezing locks away excess moisture. The delicate balance between solid and liquid water creates the stable hydrological cycle that complex ecosystems require. As we drift deeper into this vision of Mars transformed, we see a world that is neither Earth nor the Mars we know today, but something entirely new. It's a hybrid planet where the familiar laws of physics and chemistry play out under alien conditions, creating landscapes and ecosystems that have never existed before in the universe. The red planet slowly becomes something more subtle, its color shifting from rust to ochre to the varied hues of life. Green spreads across its surface in patches and ribbons, following the watercourses and favorable microclimates. The sky, no longer the pale butterscotch of the thin atmosphere, deepens toward blue as the atmospheric density increases, though it may never achieve the deep azure of Earth's skies. This transformation represents more than just the engineering of a world. It's the expansion of life itself beyond the boundaries of its birth planet, the first tentative steps toward making the universe a more living place. In this vision of Mars reborn, we see reflected humanity's deepest aspirations, our desire to nurture life and create beauty, even in the most challenging environments. The sleeping planet awakens not with violence, but with the gentle persistence of life itself, each day bringing small changes that accumulate over time into something magnificent. The transformation of Mars's atmosphere represents perhaps the most delicate phase of the entire terraforming process. As the initial greenhouse warming reaches its critical threshold, typically occurring several centuries into the project. The planet begins to exhibit the first signs of atmospheric thickening that will eventually support more complex life forms. The process begins with the gradual sublimation of carbon dioxide from the polar ice caps. As temperatures rise by just a few degrees, vast quantities of frozen carbon dioxide transition directly from solid to gas, adding substantial volume to the thin Martian atmosphere. This isn't a violent or dramatic process, but rather a slow, steady release that occurs over decades. The southern polar cap, containing approximately 16 billion tons of carbon dioxide ice, becomes a massive atmospheric reservoir, slowly feeding into the planet's changing climate system. Simultaneously, the permafrost across Mars's middle latitudes begins its own transformation. Beneath the surface, layers of water ice mixed with soil start to thaw, releasing not only water vapor, but also trace amounts of methane, ammonia, and other greenhouse compounds that have been locked away for millennia. This subsurface melting creates a feedback loop, where each increment of warming releases more greenhouse gases, which in turn accelerate the warming process. The atmospheric pressure, initially less than 1% of Earth's, gradually increases as these reservoirs contribute their contents to the sky above. At first, the changes are barely measurable, requiring sensitive instruments to detect the subtle shifts in pressure and composition. But as the decades pass, the atmosphere begins to hold more heat, creating increasingly stable weather patterns and reducing the extreme temperature fluctuations that characterize present-day Mars. During this phase, the engineered microorganisms that were introduced in the earlier stages of terraforming begin to flourish. These specially designed bacteria and archaea, modified to survive in the harsh Martian environment, start converting atmospheric carbon dioxide into oxygen through photosynthesis. Their populations, initially constrained by the planet's hostile conditions, begin to expand exponentially as the environment becomes more hospitable. The most successful of these organisms are the extremophils, Earth bacteria that have been genetically enhanced to thrive in Mars's unique conditions. Some varieties process sulfur compounds found in Martian soil, while others specialize in breaking down perchlorates, the toxic chemicals that make much of the Martian surface sterile. As these microorganisms spread across the planet's surface, they begin the slow work of soil remediation, gradually neutralizing the chemical hazards that would otherwise prevent more complex life from taking hold. The introduction of photosynthetic organisms marks a crucial milestone in atmospheric development. Cyanobacteria, the same type of organisms that first oxygenated Earth's atmosphere billions of years ago, are among the first to establish stable populations on Mars. These hardy microbes form thin mats across areas where liquid water becomes available, creating the first visible signs of life that future colonists might observe with the naked eye. As the atmospheric pressure increases and temperatures stabilize, water begins to play an increasingly important role in the transformation. The first liquid water appears in the deepest basins and crater floors, where the combination of increased atmospheric pressure and rising temperatures allows ice to melt and remain liquid for extended periods. These initial pools of water, often highly saline due to dissolved minerals in the Martian soil, become the planet's first permanent liquid reservoirs since its ancient past. The water cycle, absent from Mars for billions of years, slowly begins to reassert itself. Water vapor, released from melting permafrost and sublimating ice, begins to participate in weather patterns. The first Martian clouds in geological ages start to form, though they remain sparse and ephemeral. Occasionally, these clouds produce the planet's first precipitation, usually in the form of light snow or frost that quickly sublimates back into the atmosphere. Plant life introduction begins during this phase, though it requires careful selection and genetic modification to succeed. The first terrestrial plants to take root on Mars are typically hardy species like certain mosses, lichens, and specially engineered grasses that can tolerate the planet's still challenging conditions. These pioneer species are chosen for their ability to survive in low-pressure environments, tolerate high levels of ultraviolet radiation, and thrive in the alkaline soils that characterize much of Mars's surface. The establishment of these first plant communities represents a profound shift in Mars's ecological trajectory. Plants not only contribute oxygen to the atmosphere through photosynthesis, but also help stabilize soil through their root systems, preventing erosion and creating microenvironments where other organisms can establish themselves. The organic matter they produce when they die begins to enrich the previously sterile Martian soil, creating the foundation for more complex soil ecosystems. As plant communities expand, they begin to modify their local environments in subtle but important ways. Vegetation creates microclimates with different temperature and humidity conditions than surrounding bare ground. These vegetated areas become islands of biological activity where modified Earth organisms and indigenous Martian life, if it exists, can interact and potentially co-evolve. The atmospheric oxygen concentration, while still far below Earth levels, begins to reach thresholds where certain types of complex life can survive with minimal technological assistance. The first small invertebrates, carefully selected and modified for Martian conditions, are introduced to areas where plant communities have become established. These might include certain types of worms, arthropods, and other creatures that can help break down organic matter and contribute to soil development. Soil formation accelerates dramatically during this phase. The combination of microbial activity, plant growth and decay, and physical weathering processes begins to transform the sterile Martian regolith into something resembling actual soil. This process, which took millions of years in Earth's natural history, is accelerated through careful management and the introduction of Earth organisms specifically chosen for their soil-building capabilities. The magnetic field consideration becomes increasingly important as the atmosphere thickens. Mars's lack of a global magnetic field means that solar wind continues to strip away atmospheric particles, though at a slower rate as the atmosphere becomes denser. Various proposals for addressing this challenge, from orbital magnetic field generators to surface-based installations, would likely be implemented during this phase to protect the growing atmosphere from continued erosion. Regional climate variations begin to emerge as the atmosphere develops complexity. Areas near the equator experience more dramatic temperature swings, while polar regions remain cold but begin to develop their own unique weather patterns. The massive canyon systems like Valles Marineris create their own microclimates as air circulation patterns develop within these geographical features. The planet's two small moons, Phobos and Deimos, begin to have subtle but measurable effects on the developing atmosphere. Their gravitational influence, while weak compared to Earth's moon, creates small tidal effects in the thickening atmosphere that contribute to global circulation patterns. As this atmospheric development phase progresses over several centuries, Mars gradually transitions from a cold, nearly airless world to a planet with a thin but breathable atmosphere, at least at lower elevations. The transformation isn't uniform across the planet's surface, with some regions developing faster than others based on factors like elevation, latitude, and local geological conditions. The transformation of Mars into a habitable world would continue its spectacular evolution as the centuries unfold. By now, the atmospheric thickening has reached a critical threshold where new phenomena begin to emerge. Phenomena that would reshape not just the planet's appearance, but its very character as a world. The dust storms that once scoured Mars with relentless fury would gradually transform into something more familiar, yet distinctly Martian. As atmospheric pressure builds and water vapor increases, these storms would begin to carry moisture, occasionally producing the planet's first tentative rainfall in billions of years. Picture these early Martian storms, still tinged with the russet dust that gives the planet its character, but now punctuated by the gentle patter of precipitation on newly formed soils. The polar ice caps, those pristine white crowns that have adorned Mars for eons, would continue their dramatic retreat and transformation. What was once solid carbon dioxide and water ice would increasingly become liquid, flowing toward the equatorial regions through networks of channels that mirror, in some ways, the ancient riverbeds that once carried water across primordial Mars. These flows would carve new geological features, creating a landscape that blends the ancient and the nascent in ways that would be hauntingly beautiful to witness. As liquid water becomes more stable on the surface, the first permanent bodies of water would begin to form. Initially, these might be little more than seasonal ponds that freeze and thaw with Mars's long seasons, but gradually they would grow into lakes and eventually small seas. The northern lowlands, those vast basins that may have once held an ancient ocean, would slowly begin to fill again. The sight of sunlight glinting off Martian lakes, with the towering bulk of Olympus Mons visible on the horizon, would represent one of the most profound transformations in planetary history. The emerging hydrological cycle would create weather patterns entirely unique to Mars. The planet's lower gravity means that water droplets would fall more slowly through the thickening atmosphere, creating precipitation events that might last for days. Cloud formations would develop their own Martian characteristics, influenced by the planet's rapid temperature changes between day and night, and its dramatic seasonal variations caused by the elliptical orbit and axial tilt. The microbial communities that began this transformation would now face new challenges and opportunities. As liquid water becomes more available, competition between different microorganisms would intensify. Some would specialize in the newly formed soils, breaking down the iron oxides that give Mars its red color and releasing nutrients that could support more complex biochemistry. Others would colonize the growing bodies of water, forming the foundation of the first truly aquatic ecosystems on Mars in billions of years. Plant life, still in its pioneering phase, would begin to diversify and spread beyond the protected valleys and crater floors where it first took hold. Hardy grasses and moss-like organisms would creep across the landscape, their root systems helping to bind the loose regolith into more stable soil. The first shrubs might appear, adapted to Mars' unique challenges, with specialized root systems that can reach deep underground for water and nutrients, and waxy leaves that can withstand the still harsh temperature fluctuations. The transformation of Mars' atmosphere would accelerate as these biological processes gain momentum. The oxygen, being produced by countless photosynthetic organisms, would begin to reach concentrations that could support simple animal life. The first invertebrates might be introduced or evolved from the microbial communities, tiny creatures that could process the increasingly complex organic compounds being produced by the expanding ecosystem. These early animals would be unlike anything on Earth, adapted to Mars' unique conditions in ways that would seem almost alien to terrestrial observers. Lower gravity would allow for body structures that would be impossible on Earth, while the different atmospheric composition would require novel approaches to respiration and metabolism. Some might develop symbiotic relationships with the photosynthetic organisms, carrying algae or bacteria within their bodies to supplement their energy needs. The geological activity that helps drive this transformation would continue to play a crucial role. Volcanic outgassing would contribute additional water vapor and carbon dioxide to the atmosphere, while the planet's internal heat would help maintain liquid water reservoirs beneath the surface. The interplay between biological and geological processes would create feedback loops that accelerate the transformation, each reinforcing the other in a complex dance of planetary evolution. As Mars's magnetic field situation improves, whether through technological intervention or natural processes, the atmosphere would become more stable and better protected from solar radiation. This protection would allow for more complex chemistry to occur in the upper atmosphere, potentially leading to the formation of an ozone layer that could shield the surface from harmful ultraviolet radiation. The seasonal cycles on Mars would become more pronounced and meaningful as the planet develops weather systems similar to those on Earth. The long Martian seasons, each lasting roughly 6 Earth months, would create dramatic annual cycles of growth and dormancy, flooding and drought that would shape the evolution of life on the planet. Spring on Mars might bring massive migrations of organisms as ice melts and water flows toward the equator, while winter could see widespread dormancy and adaptation to the harsh cold. The human settlements that would witness these changes would need to adapt their strategies and technologies as Mars transforms around them. Early colonies designed for survival in a hostile environment would gradually evolve into communities that could work with and within the developing ecosystem. Agricultural practices would shift from closed-system hydroponics to working with Martian soils and climate patterns. The psychological and cultural impact of witnessing a planet come alive would be profound for these human inhabitants. They would be living through the most dramatic transformation in the solar system's history, watching as a dead world slowly awakens. The red planet that their ancestors knew would gradually give way to something new, something that has never existed before in the 4.5 billion year history of Mars. Regional variations would become more pronounced as different areas of Mars develop their own unique characteristics. The Great Canyon system of Valles Marineris might become a vast river valley, while the volcanic regions could host unique ecosystems adapted to geothermal heat. The polar regions would remain distinct, perhaps maintaining ice caps year-round while supporting their own specialized communities of life. The transformation would not be uniform or predictable. Some areas might experience rapid changes, while others remain stubbornly resistant to transformation. Setbacks would occur, perhaps from dust storms that temporarily reverse local progress, or from the complex interactions between different introduced species. The process would be messy, chaotic, and sometimes surprising, as all natural processes tend to be. As this great work continues across the centuries, Mars would slowly transition from a world where life struggles to survive to one where it begins to thrive. The planet would develop its own unique character, neither fully Earth-like nor remaining the barren Mars of old, but something entirely new in the cosmos. Part 7. The Dance of Weather and Seasons. Over the centuries and millennia that follow the initial terraforming efforts, Mars begins to develop something that has been absent from its surface for billions of years. Weather patterns that cycle and change with predictable rhythms. As the atmosphere thickens and water becomes more abundant, the planet starts to experience its own unique meteorological symphony, one that differs dramatically from Earth's familiar patterns, yet follows the same fundamental principles of atmospheric physics. The Martian day, lasting 24 hours and 37 minutes, creates a rhythm not entirely unlike Earth's, but the planet's greater distance from the Sun and its elliptical orbit produce seasons that stretch nearly twice as long as those we know. Spring on Mars unfolds over the course of 7 Earth months, a languid awakening that allows the newly established ecosystems to gradually adjust to changing temperatures and light conditions. Summer brings intense but brief periods of warmth to the equatorial regions, while the polar areas experience a gentler warming that slowly releases more water vapor into the thickening atmosphere. The unique topography of Mars creates microclimates that would be impossible on any other world. The massive canyon system of Valles Marineris, stretching over 4,000 kilometers across the planet's surface, becomes a vast atmospheric highway where winds accelerate and moisture collects. During the warmer months, Morning mists rise from the canyon floors where underground springs have been coaxed to the surface by human engineering. These mists carry with them the scents of the first Martian forests. Genetically modified trees that have learned to thrive in the thin air and iron-rich soil. The great shield volcanoes, though long dormant, create their own weather systems as atmospheric moisture encounters their massive slopes. Olympus Mons, rising 21 kilometers into the Martian sky, pierces through much of the lower atmosphere, creating a rain shadow effect that leaves its western slopes dry, while its eastern flanks receive the first regular precipitation that Mars has seen in geological ages. These rains are gentle affairs, more like the mists of a Scottish highland than the thunderstorms of Earth, but they are sufficient to support the spreading moss-like ground cover that has been engineered to bind the soil and prevent erosion. As the decades pass, more complex weather patterns begin to emerge. The interaction between the planet's two small moons, Phobos and Deimos, creates subtle tidal effects in the atmosphere that become more pronounced as the air grows denser. These atmospheric tides produce gentle, predictable wind patterns that the early Martian farmers learned to anticipate and utilize. Windmills designed for the thin Martian air begin to dot the landscape, their slowly turning blades generating power, while their presence creates small eddies and updrafts that help distribute moisture and seeds across the gradually greening terrain. The dust storms that once raged across the entire planet for months at a time become smaller and more localized as vegetation begins to anchor the soil. What were once global atmospheric catastrophes transform into regional weather events that, while still dramatic, no longer threaten to engulf the entire world. These storms take on a different character as well, carrying with them not just the sterile dust of ancient impact craters, but the pollen and spores of the new Martian biosphere. What was once destruction becomes distribution, spreading life rather than death across the red landscape. The polar ice caps, no longer just frozen carbon dioxide, begin to cycle water in patterns that create the planet's first true seasons. As the northern ice cap melts during the Martian summer, vast quantities of water vapor enter the atmosphere, creating cloud formations that would have been impossible in the planet's previous incarnation. These clouds, tinged with the rusty hues of iron-rich dust, create spectacular sunsets that rival those of Earth, painting the Martian sky in shades of gold, orange, and deep purple that gradually fade to the familiar butterscotch of the daytime atmosphere. The first Martian snow falls gently on the highland regions, creating scenes of ethereal beauty as the white crystals settle on the rust-colored rocks and the hardy alpine plants that have begun to colonize the higher elevations. This snow is different from Earth's frozen precipitation, forming in the thin atmosphere and falling more slowly due to the planet's reduced gravity. It accumulates in the sheltered valleys and crater floors, creating temporary lakes and streams as it melts during the brief Martian spring. Temperature variations across the planet become less extreme as the atmosphere thickens and retains more heat. The equatorial regions, once scorching during the day and freezing at night, develop more moderate temperature swings that allow for the establishment of stable ecosystems. The polar regions, while still cold, no longer experience the bone-chilling temperatures that once made them utterly inhospitable to any form of life. These temperature changes happen gradually, over periods measured in centuries rather than decades, giving both the engineered organisms and any naturally occurring life forms time to adapt and evolve. The interaction between the planet's magnetic field, artificially strengthened through technological intervention, and the solar wind creates aurora displays that dance across the Martian night sky. These lights are more frequent and intense than Earth's aurora due to Mars's thinner atmosphere and different magnetic field configuration. They appear in colors rarely seen on Earth, including deep purples and brilliant greens that reflect the unique composition of the Martian atmosphere. These displays become one of the most beloved features of the Martian night, inspiring the planet's first poets and artists to create works that capture the alien beauty of their new world. Atmospheric pressure continues to increase slowly, reaching levels that allow liquid water to remain stable at increasingly higher elevations. This change enables the establishment of mountain lakes and highland streams, creating habitats for aquatic organisms that have been modified to thrive in the cold, mineral-rich waters. These high-altitude ecosystems become crucial nurseries for the planet's developing hydrological cycle, serving as reservoirs that regulate water flow and provide habitat for increasingly complex food webs. The chemistry of precipitation changes as the atmosphere evolves. Early Martian rain is highly acidic due to the dissolution of atmospheric carbon dioxide and the presence of sulfur compounds from the planet's volcanic past. However, as plant life spreads and begins to buffer the soil and water systems, the pH gradually normalizes. The rain becomes less corrosive and more life-supporting, carrying with it the nutrients needed to sustain the expanding biosphere. Wind patterns stabilize into recognizable systems as the planet's rotation and the distribution of land and water create more predictable circulation patterns. Trade winds develop in the equatorial regions, while the polar areas experience their own characteristic circulation patterns. These winds carry moisture, seeds, and nutrients across vast distances, helping to spread life to previously barren regions and connecting distant ecosystems into a planet-wide web of biological exchange. Seasonal migration patterns begin to emerge among the more mobile organisms as different regions of the planet experience optimal conditions at different times of the Martian year. Flying insects, eventually followed by small vertebrates, begin to move in response to temperature changes, rainfall patterns, and the availability of food sources. These migration patterns create corridors of biological activity that further connect the planet's scattered ecosystems and promote genetic exchange between populations. The development of weather prediction becomes crucial for the human settlers and their agricultural endeavors. Meteorological stations scattered across the planet begin to detect and track the emerging patterns, creating the first Martian weather forecasts. These predictions are initially crude and often inaccurate, as the planet's weather systems are still stabilizing and the scientists are learning to interpret atmospheric conditions that have no direct parallel on Earth. Cloud formation becomes increasingly common as atmospheric moisture content rises. These clouds are initially thin and ephemeral, but as the atmosphere continues to thicken, they become more substantial and long-lasting. The sight of white clouds drifting across the butterscotch Martian sky becomes a symbol of the planet's transformation, a visual reminder that this world is no longer the desiccated desert it once was. The interaction between surface water and the atmosphere creates localized humidity zones that support different types of vegetation. Areas around lakes and rivers develop their own microclimates, often significantly more humid and temperate than the surrounding regions. These oases become centers of biological diversity and human settlement, creating a patchwork of green zones connected by the gradually expanding transportation and communication networks. Lightning begins to occur during the more intense weather events, though it is initially rare and weak due to the still thin atmosphere. As atmospheric density increases, electrical activity becomes more common, creating spectacular displays during the larger storm systems. This lightning serves an important biological function, fixing nitrogen in the atmosphere and making it available to plants, further accelerating the development of the Martian biosphere. The planet's weather systems begin to influence human culture and society in ways both practical and profound. Agricultural cycles adapt to the long Martian seasons, with crop rotations planned around the extended growing periods and the predictable patterns of precipitation and temperature change. Architecture evolves to take advantage of seasonal wind patterns for cooling and heating, while settlements are positioned to benefit from favourable microclimates and to shelter from the occasional severe weather events. As this great atmospheric transformation continues across the centuries, Mars slowly sheds its identity as the red planet of ancient mythology and begins to earn a new designation as a world of changing skies, shifting seasons, and the gentle rhythms of weather that make complex life possible. The transformation of Mars through centuries of terraforming continues to unfold in remarkable ways. As the atmospheric pressure stabilizes and the water cycle becomes more robust, we begin to witness the emergence of what might be called Mars's first true seasons. These are not the subtle variations driven purely by orbital mechanics that characterize the planet's ancient past, but rather dynamic seasonal changes born from the interaction of a thickening atmosphere with the planet's unique geography. The Great Canyon systems of Mars, particularly Valles Marineris, begin to play an increasingly important role in the planet's developing weather patterns. This massive rift, stretching over 4,000 kilometers across the Martian surface, creates a natural corridor for atmospheric circulation. As the sun heats the canyon walls during the Martian day, warm air rises and creates updrafts that can be felt hundreds of kilometers away. These thermal currents, combined with the planet's gradually strengthening magnetic field, begin to generate the first sustained wind patterns in Mars's modern history. The polar regions, once locked in eternal winter, now experience genuine seasonal variation. During the Northern Hemisphere's spring, the retreating ice cap releases vast quantities of water vapor into the atmosphere, creating spectacular cloud formations that can be seen from orbit. These clouds, initially thin and ephemeral, gradually become more substantial as the atmospheric pressure increases. They cast shadows across the rust-coloured landscape below, creating the first true shade that Mars has known in millions of years. As these seasonal patterns establish themselves, they begin to influence the distribution of the hardy microorganisms that now call Mars home. The extremophiles that were first introduced to the planet have evolved and adapted, developing new strategies for surviving the planet's still challenging conditions. Some species have learned to enter dormancy during the coldest periods, while others have developed the ability to migrate with the changing seasons, following the melting ice and the brief blooms of liquid water that appear in the planet's lower elevations. The emergence of these seasonal migrations represents a turning point in Mars's biological development. For the first time since the planet's ancient past, life moves across its surface in response to environmental cues. Microscopic organisms that cluster around geothermal vents during the winter months spread outward as temperatures rise, colonizing new areas and establishing the foundations for more complex ecosystems. The interaction between the developing biosphere and the planet's geology creates feedback loops that accelerate the terraforming process. As microorganisms break down rocks and release nutrients into the primitive soil, they create conditions that are more favorable for plant life. The first genetically modified lichens and mosses, designed to thrive in Mars's low oxygen environment, begin to establish small colonies on the planet's surface. These pioneering plants, though tiny and seemingly insignificant, represent a profound shift in Mars's character. The presence of photosynthetic organisms, even in small numbers, begins to alter the composition of the atmosphere in subtle but measurable ways. Oxygen levels, while still far below Earth standards, begin to show detectable increases in areas where plant life has taken hold. The carbon dioxide that makes up the bulk of Mars's atmosphere slowly begins to be converted into organic compounds, creating the first truly Martian soil, rich in carbon-based molecules. As the seasons progress, The interplay between the atmosphere, hydrosphere, and biosphere becomes increasingly complex. The dust storms that once raged across the planet with devastating force begin to moderate as the thicker atmosphere provides greater thermal stability. While storms still occur, they are less frequent and less severe, allowing the delicate plant communities to establish deeper root systems and more permanent colonies. The development of weather patterns also creates new opportunities for human settlements. The early colonists, who had lived in sealed habitats and relied entirely on artificial life support systems, begin to take advantage of the changing atmospheric conditions. Greenhouse structures can now be built with lighter materials, as the external pressure differential is no longer as extreme. Water harvesting becomes more efficient as the predictable seasonal patterns allow for better planning and resource management. The first experimental outdoor agriculture begins during this period, with heavily modified crops growing in specially prepared soil under protective domes. These early farms, while still dependent on significant technological support, represent humanity's first attempt to truly live off the land on Mars. The psychological impact of this development cannot be overstated. For the first time, humans on Mars are not merely surviving, but beginning to thrive, drawing sustenance from the planet itself rather than from supplies shipped from Earth. The changing atmospheric conditions also affect the planet's thermal dynamics in profound ways. The increased atmospheric density allows for better heat retention, reducing the extreme temperature variations that once characterized Mars. While the planet is still cold by Earth standards, the difference between day and night temperatures becomes less severe, creating more stable conditions for both biological and technological systems. As the water cycle strengthens, the first permanent bodies of liquid water begin to appear on Mars's surface. These are not the vast oceans that may have existed in the planet's distant past, but rather modest lakes and ponds that form in the lowest elevations. The water is often highly saline and contains dissolved minerals that would be toxic to most Earth life, but it represents a crucial step in Mars's hydrological development. The formation of these water bodies creates new micro-environments that support different types of life. Halophilic organisms, which thrive in high salt conditions, begin to colonize the shores of these primitive lakes. These microorganisms, adapted to extreme salinity, process the dissolved minerals and begin to create the chemical gradients that will eventually support more complex aquatic ecosystems. The presence of standing water also affects local weather patterns, creating microclimates that are markedly different from the surrounding desert. Evaporation from these water bodies increases local humidity, which in turn affects temperature regulation and creates opportunities for different types of organisms to establish themselves. The areas around these lakes become oases of relative abundance in the otherwise harsh Martian landscape. As the centuries pass, the cumulative effects of these changes begin to transform Mars from a dead world into something approaching a living planet. The red color that has defined Mars for millennia begins to fade in places, replaced by the browns and greens of soil enriched with organic matter and the first primitive vegetation. The planet's famous dust storms, while still occurring, no longer have the power to completely obscure the surface for months at a time. The magnetic field, strengthened by the planet's gradually increasing rotation and the movement of its molten core, begins to provide better protection from solar radiation. This improvement in the radiation environment allows for more sophisticated life forms to evolve and enables human settlements to expand beyond the heavily shielded habitats of the early colonial period. The development of Mars's biosphere also creates new challenges and opportunities for human civilization. The need to protect the emerging ecosystems from contamination becomes a priority, leading to the development of new technologies and protocols for human activity on the planet. At the same time, the growing biological productivity of Mars begins to provide resources that can support larger human populations. The transformation of Mars during this period represents a unique moment in the history of both planets. Never before has a world undergone such rapid and comprehensive change through the deliberate intervention of an intelligent species. The lessons learned from this vast experiment in planetary engineering will inform humanity's relationship with both Mars and Earth for generations to come. As we look toward the future of this transformed Mars, we can see the foundations being laid for a world that will be neither Earth nor the ancient Mars, but something entirely new. The transformation of Mars extends far beyond atmospheric chemistry and biological colonization into something altogether more profound, the gradual emergence of distinctly Martian cultures and societies that will differ fundamentally from their Earthborn origins. As the centuries pass and the terraforming process continues its slow work, the human settlements scattered across the red planet begin to develop their own unique characteristics, shaped by the peculiar demands of life on a world caught between its ancient desolation and its emerging vitality. The early Martian colonies, established during the planet's harshest phase, were necessarily focused on mere survival, their inhabitants living in sealed habitats and depending entirely on technological life support systems. These pioneers developed a culture of extreme pragmatism and cooperation, where individual preferences were subordinated to collective survival and every resource was precious beyond measure. The social structures that emerged from these early settlements were characterized by rigid hierarchies based on technical expertise and resource management, with decisions made through careful consensus building that could mean the difference between life and death for entire communities. As the atmosphere gradually thickens and the first primitive ecosystems take hold, these survival-focused cultures begin to evolve and differentiate. The settlements near the polar regions, where the first significant water sources become readily available, develop societies that revolve around agricultural cycles and water management. Their social calendars, marked by planting seasons and harvest festivals that celebrate the miraculous emergence of life from previously sterile soil. These polar communities become known for their elaborate greenhouse complexes and their deep knowledge of hydroponic systems, developing traditions that blend ancient Earth agricultural practices with the unique demands of Martian farming. The equatorial settlements, positioned to take advantage of the planet's most stable weather patterns, evolve into centers of commerce and communication, their inhabitants becoming the traders and diplomats who maintain connections between distant colonies. These communities develop more cosmopolitan cultures, welcoming travelers and maintaining libraries and communication networks that preserve knowledge from across the planet. Their social structures are more fluid and merit-based, with status determined by one's ability to facilitate trade and maintain the complex logistical networks that keep the scattered settlements supplied with necessary goods and information. The highland settlements, perched on the ancient volcanic peaks and crater rims, develop cultures that emphasize exploration and scientific research, their inhabitants becoming the planet's primary surveyors and atmospheric monitors. These communities maintain the most direct connections with Earth through their communication arrays and research stations, and they develop traditions that blend scientific methodology with something approaching mysticism, as they observe and document the planet's gradual transformation from their elevated vantage points. Their social hierarchies are based on scientific achievement and exploration accomplishments, with the most respected members being those who have mapped new territories or made significant discoveries about the planet's changing ecosystem. As Mars's transformation progresses and travel between settlements becomes safer and more routine, these different colonial cultures begin to interact more extensively, leading to the emergence of a distinctly Martian identity that transcends individual settlement origins. This planetary culture develops its own language variations, incorporating technical terms related to atmospheric management and terraforming alongside borrowed words from the various Earth languages represented among the colonists. The Martian dialect becomes characterized by its precision and efficiency, reflecting the planet's ongoing need for clear communication about complex technical and environmental matters. The arts that emerge on Mars reflect the planet's unique aesthetic environment and cultural priorities. Martian music incorporates the sounds of atmospheric processes and wind patterns, creating compositions that would sound alien to Earth-born listeners, but feel natural to those who have grown up with the constant background hum of terraforming equipment. Visual arts celebrate the dramatic landscapes created by the interaction between ancient Martian geology and new biological systems, with painters and sculptors finding inspiration in the stark contrast between sterile rock formations and emerging oases of life. Literature and storytelling traditions develop that focus on themes of transformation and adaptation, with popular narratives exploring the psychological and social challenges of living on a world that changes perceptibly within single lifetimes. These stories often feature protagonists who must navigate between old ways of thinking, rooted in survival necessity, and new possibilities opened by the planet's increasing habitability. The most celebrated Martian authors are those who can capture the unique experience of watching a world come alive, of being present for the emergence of ecosystems and weather patterns that no human has ever witnessed before. Religious and philosophical movements that emerge on Mars tend to focus on humanity's relationship with planetary systems and the ethics of terraforming. Some Martian spiritual traditions develop around the idea of partnership with the planet itself, viewing the terraforming process as a collaboration between human technology and Martian potential, rather than simply the imposition of Earth-like conditions on an alien world. These belief systems often incorporate rituals and practices designed to honor both the planet's ancient history and its emerging future, creating ceremonies that mark significant milestones in the atmospheric transformation process. The political structures that evolve on Mars reflect both the planet's distributed settlement pattern and the ongoing need for coordinated environmental management. Rather than developing traditional nation-states, Martian governance tends toward federal systems that balance local settlement autonomy with planet-wide coordination on atmospheric and ecological management. These political arrangements are characterized by their technical orientation, with many governmental decisions being made by councils of scientists and engineers rather than traditional politicians, reflecting the reality that poor environmental management decisions could still threaten the survival of all Martian life. Educational systems on Mars develop distinctive characteristics that reflect the planet's unique needs and opportunities. Martian children grow up learning not just traditional academic subjects, but also atmospheric science, ecosystem management, and the history of terraforming, creating generations that understand their planet's transformation as an ongoing process in which they are active participants. These educational programs emphasize adaptability and systems thinking, preparing students for lives on a world where environmental conditions continue to change and where understanding complex interactions between technology and biology is essential for both personal and community survival. As the terraforming process advances and Mars becomes increasingly Earth-like in its basic habitability, tensions sometimes emerge between those who advocate for complete terrestrial transformation and those who believe Mars should retain some of its unique characteristics. These debates reflect deeper questions about planetary identity and the goals of human expansion into space, with some Martians arguing that their world should become as Earth-like as possible to support maximum population and economic development, while others contend that Mars should maintain its distinctive features and develop along its own unique evolutionary path. The resolution of these tensions often comes through practical experience rather than theoretical debate, as Martian communities discover that the planet's transformation creates opportunities for ways of life that are neither strictly terrestrial nor traditionally Martian, but something entirely new. The successful integration of human civilization with Mars's emerging ecosystems requires innovations in agriculture, architecture, and social organization that draw from Earth experience while adapting to Martian realities, creating hybrid approaches that prove more effective than either purely traditional or purely technological solutions. Over time, as communication delays and the practical difficulties of interplanetary travel create increasing separation between Mars and Earth, Martian culture develops its own momentum and direction, influenced by but not dependent on terrestrial trends and developments. This cultural independence reflects the planet's growing environmental independence, as Mars develops self-sustaining ecosystems and atmospheric cycles that no longer require constant technological intervention to maintain habitability. The emerging Martian civilization represents humanity's first successful adaptation to life on another world, demonstrating both the species' remarkable adaptability and the possibility of creating sustainable human presence beyond Earth. As Mars continues its transformation from a lifeless desert into a living world, its human inhabitants evolve alongside the planet itself, developing new forms of culture, governance, and social organization that reflect the unique challenges and opportunities of life on a terraformed world. The transformation we've been witnessing on Mars isn't happening in isolation. As the planet gradually awakens from its ancient slumber, something remarkable begins to emerge from the convergence of all these changes. The thickening atmosphere, the flowing water, the spreading life, the evolving landscapes, and the growing human communities start to weave together into something entirely new. A planetary identity begins to form, as unique and distinctive as Earth's blue marble appearance, yet utterly its own. Picture Mars several centuries into its transformation. The morning sky carries a subtle warmth that wasn't there before, tinted with wisps of clouds that catch the early light. The air, while still thin by Earth standards, has grown substantial enough to carry scents. There's the mineral tang of dust stirred by increasingly complex weather patterns, the green freshness of photosynthetic organisms processing the atmosphere, and occasionally, the sweet dampness that precedes precipitation. The planet's surface tells a story of gradual awakening. Ancient riverbeds that lay dormant for billions of years now carry seasonal streams, their banks lined with increasingly sophisticated plant communities. These aren't Earth plants struggling to survive in alien conditions, but organisms that have found their perfect home in Mars's unique environment. They've adapted to the longer seasons, the different light spectrum, the mineral-rich soils that taste of iron and sulfur. Some regions develop their own distinctive characters. The vast Amazonas planitia becomes known for its rolling grasslands, where specially adapted grasses wave in the thin but increasingly active atmosphere. These plants have evolved extraordinary root systems that can tap into subsurface water reserves, creating an ecosystem that thrives during the long Martian seasons. When spring arrives in this region, lasting nearly twice as long as an Earth season, the plains transform into a carpet of subtle colours, not the vibrant greens of Earth, but something more muted, more perfectly suited to the filtered sunlight. The polar regions develop their own unique beauty. As the ice caps slowly shrink and seasonal patterns become more pronounced, they create spectacular displays. The retreating ice reveals landscapes carved by ancient glacial activity, now slowly coming to life as temperatures rise and water becomes more available. Hardy organisms, some descended from Earth's extremophiles but now thoroughly Martian, create communities around the warming ice margins. They form colourful mats and crusts that paint the landscape in unexpected hues. Perhaps most remarkably, the Great Canyon system of Valles Marineris becomes Mars's most dramatic ecosystem showcase. The canyon's depth creates a range of microclimates, from the relatively warm and humid canyon floor to the cooler, more arid rim regions. As atmospheric pressure increases, the canyon begins to trap moisture and warmth, creating its own weather patterns. Clouds form within the canyon system, bringing precipitation to different levels at different times. The result is a layered ecosystem with different communities of organisms adapted to each level's unique conditions. Water, that most precious resource, begins to flow more freely across the Martian landscape. Not in rushing torrents like Earth's rivers, but in a more measured, patient way that suits Mars's character. Springs emerge in crater walls where underground aquifers meet the surface. These create small oases that become focal points for both biological and human activity. The water carries dissolved minerals that give it a distinctive taste and colour, creating streams that might run rust red with iron or pale blue-green with copper compounds. The human settlements scattered across this transforming world begin to develop their own cultural responses to these changes. Communities that started as purely functional outposts gradually developed traditions and celebrations tied to Mars's unique rhythms. They mark the first appearance of clouds in their region, celebrate the annual awakening of local water sources, and develop festivals around the planet's distinctive seasonal transitions. Architecture evolves to embrace rather than merely withstand the Martian environment. Early structures were built to exclude Mars, to create little bubbles of Earth-like conditions. But as the planet becomes more hospitable, buildings begin to incorporate the outside world. Large windows become common, allowing inhabitants to watch the play of light through the gradually thickening atmosphere. Gardens and courtyards open to the Martian air become gathering places. The distinctive red-orange light of Mars begins to influence artistic movements, with local artisans learning to work with materials that capture and reflect this unique illumination. The night sky becomes a source of particular wonder. Earth hangs as a brilliant blue star, visible to the naked eye and a constant reminder of humanity's origins. But Mars's two small moons, Phobos and Deimos, racing across the star-filled sky, create a celestial dance unlike anything seen from Earth. As the atmosphere thickens, it begins to scatter light in new ways, creating subtle auroras when solar particles interact with Mars's weak magnetic field. Weather, once virtually non-existent on Mars, becomes an increasingly important part of daily life. Dust storms still occur, but they're now interspersed with other phenomena. Rain becomes possible in some regions, though it's often a light, misty precipitation quite different from Earth's downpours. Snow falls more regularly at the poles and in elevated regions, but it's a mixture of water and carbon dioxide that creates unique crystal formations. The transformation isn't uniform across the planet. Different regions develop their own personalities based on their geography, geology, and the particular mix of organisms that find homes there. The great shield volcanoes like Olympus Mons create their own weather patterns, with clouds forming around their peaks and unique ecosystems developing on their vast slopes. The impact craters become individual worlds unto themselves, each with its own microclimate and community of life. Perhaps most importantly, Mars begins to develop its own distinctive relationship with time. The planet's longer day and longer year create rhythms unlike those of Earth. Human communities adapt to these rhythms, developing work patterns, social customs, and even biological adaptations that align with Mars's temporal signature. Children born on Mars grow up with an intuitive understanding of these longer cycles, developing a patience and perspective that reflects their world's more measured pace. The planet's growing biosphere creates increasingly complex interactions. Organisms that arrive separately begin to form symbiotic relationships, creating ecological networks that are uniquely Martian. Some organisms modify the soil chemistry in ways that benefit others. Photosynthetic life forms create oxygen-rich microzones that support more complex organisms. Underground fungal networks, adapted to Mars's subsurface conditions, begin to connect distant communities of surface life. This is Mars becoming truly itself, not a pale imitation of Earth, but a world with its own character, its own beauty, its own contribution to the cosmos. The red planet is acquiring a new identity while retaining its essential Martian nature. It's a world where the horizon is always tinged with that distinctive rusty hue, where the sunsets paint the sky in colours that would seem alien on Earth but feel perfectly natural under the Martian heavens. As this transformation continues, Mars offers something precious to both its human inhabitants and the broader cosmos. It becomes a proof of concept for planetary stewardship, a demonstration that worlds can be awakened gently, that life can find new homes without erasing what came before. The terraforming engines that once roared across Mars have long since fallen silent, their massive atmospheric processes now overgrown with the very vegetation they helped nurture. Where once only dust devils danced across barren plains, gentle breezes now carry the scent of pine and wildflowers through valleys that echo with the sound of running water. This is Mars as few could have imagined it during those early centuries of patient transformation. The red planet's metamorphosis into a living world has created something entirely unique in the solar system. Neither Earth nor the Mars of old, but a hybrid realm where crimson cliffs rise above emerald meadows and ancient impact craters have become pristine lakes reflecting alien sunsets. The atmosphere, now thick enough to breathe, carries sounds that would have been impossible in the thin air of yesteryear. Birds imported from Earth call from trees that grow in Martian soil, while native organisms that evolved during the terraforming process add their own voices to this planetary symphony. Walking through New Geneva, one of the great cities that emerged in the northern plains, visitors often comment on the ethereal quality of the light. The sun, smaller and more distant than it appears from Earth, casts shadows with softer edges, while the atmosphere filters sunlight into hues that painters spend lifetimes trying to capture. The city itself rises in graceful spirals, its architecture adapted to Mars's lower gravity, allowing for structures that would be impossible on the heavier world of humanity's birth. Gardens cascade down the sides of buildings, their roots extending deep into the enriched Martian soil that took centuries to develop. The transformation of Mars required patience on a scale that challenged human nature itself. Early colonists lived and died knowing they would never see the completed vision, working instead for the promise of what their great-grandchildren might inherit. Massive atmospheric processes laboured for decades to thicken the air, while carefully designed organisms were introduced to begin the slow work of creating a biosphere. Comets were redirected to crash into the polar regions, adding water vapour to the atmosphere, and beginning the process that would eventually restore Mars's ancient water cycle. The planet's unique seasonal patterns, nearly twice as long as Earth's due to Mars's longer year, have created cultural rhythms unlike anything in human experience. Martian cities prepare for seasons that stretch across months, their inhabitants developing traditions and festivals that mark the slow progression of their extended year. Spring on Mars is a celebration that lasts for weeks, as hardy plants emerge from the long winter and the planet's surface begins its gradual warming. Summer brings the growing season, when the vast agricultural regions that now cover much of the northern hemisphere produce crops that feed not only Mars, but the asteroid colonies and outer system settlements. The polar regions of Mars have become something magnificent to behold. Where once only frozen carbon dioxide marked the changing seasons, now vast forests of cold-adapted conifers stretch toward the horizon. These northern woods, as they've come to be called, are home to creatures both familiar and strange. Earth-descended animals have adapted to the lighter gravity and thinner atmosphere, while entirely new species have emerged from the careful genetic engineering programs that helped establish the planet's ecosystem. Perhaps nowhere is Mars's transformation more evident than in the Great Canyon system of Valles Marineris. Once a stark reminder of the planet's geological violence, the canyon has become a river system that rivals the Amazon. Mist rises from waterfalls that plunge into depths that were once airless chasms, while the canyon walls support terraced cities that seem to grow organically from the rock itself. The sound of flowing water echoes constantly through these corridors, a sound that would have been impossible for most of Mars's geological history. The planet's two small moons, Phobos and Deimos, have been transformed as well. Phobos, racing across the Martian sky in its rapid orbit, now serves as a major spaceport and industrial center, its low gravity making it an ideal staging ground for missions to the outer system. Deimos, more distant and sedate, has become a haven for those seeking solitude, its surface gardens offering views of the transformed world below. Mars's unique position in the solar system has made it a crucial hub for human expansion beyond Earth. Its lighter gravity makes launching spacecraft less energy intensive than from Earth, while its position provides ideal launch windows for missions to the asteroid belt and outer planets. The planet has become humanity's second cradle, a backup for the species that has also become a launching pad for further exploration and colonization. The red planet's magnetic field, artificially generated by massive installations at the poles, protects the carefully cultivated atmosphere from the solar wind that once stripped away Mars's ancient air. These magnetic field generators, humming with constant energy, have become pilgrimage sites for many Martians, symbols of humanity's determination to give their world the protection it needs to flourish. The aurora they create, dancing in colors never seen from Earth due to Mars's different atmospheric composition, paint the night sky in curtains of green, blue, and violet light. Agriculture on Mars has evolved into something that would seem fantastical to early colonists. Vast greenhouses stretch across the landscape, their transparent domes protecting crops from the occasional dust storms that still sweep across the planet. But increasingly, hardy plants grow in the open air, their roots deep in soil that has been painstakingly created from the planet's regolith and organic matter. Martian wheat, adapted to the planet's unique conditions, grows taller than its Earth counterpart in the lighter gravity, creating golden fields that wave in the gentle Martian breeze. The planet's geological activity, once feared by early settlers, has been carefully harnessed to support the growing civilization. Mars's massive volcanoes, while dormant, provide geothermal energy that powers cities and industrial complexes. The planet's mineral wealth, exposed by billions of years of geological processes, supports a thriving mining industry that supplies raw materials not just to Mars, but to colonies throughout the solar system. Water, once the most precious resource on Mars, now flows freely across much of the planet's surface. The ancient riverbeds have been restored, fed by polar ice caps that have been carefully managed to maintain the planet's hydrological cycle. Lakes and seas, some natural and others artificially created, dot the landscape and serve as centers for recreation and transportation. The sight of sailing vessels on Martian waters, their sails filled with the planet's gentle winds, represents perhaps the most striking symbol of how completely the world has been transformed. The people of Mars have developed their own distinct culture, shaped by the unique challenges and opportunities of their world. Martian art often reflects the planet's dramatic landscapes and long seasons, with forms and styles that have no equivalent on Earth. Architecture takes advantage of the lower gravity to create soaring structures that seem to defy physics, while Martian music incorporates the unique acoustic properties of the planet's atmosphere and the rhythmic patterns of its extended days and seasons. Children born on Mars know no other world, and their perspectives often differ markedly from those of Earth-born immigrants. They move with a grace adapted to the lighter gravity, think in terms of the longer seasonal cycles, and possess an intuitive understanding of their planet's carefully balanced ecosystem. These young Martians represent something entirely new in human experience, a generation truly native to another world. The night sky above Mars tells its own story of transformation. Earth appears as a blue star in the Martian heavens, while the asteroid belt glows with the lights of mining stations and habitats. The outer planets, more prominent in Mars's sky than in Earth's, serve as beacons for the continuing expansion of human civilization. Mars has become not just humanity's second home, but the gateway to the solar system beyond. As the centuries have passed, Mars has developed its own weather patterns, distinct from both its ancient climate and Earth's familiar cycles. Clouds now gather regularly over the planet's mountain ranges, bringing rain that feeds rivers and replenishes reservoirs. Snow falls in the polar regions and on the peaks of the great volcanoes, creating winter wonderlands that attract visitors from across the solar system. The planet's dust storms, while less frequent than in the past due to the thicker atmosphere and vegetation, still occur occasionally, serving as reminders of Mars's dynamic past and present. Looking toward the future, Mars continues to evolve. The terraforming process, while largely complete, continues on a smaller scale as new regions are brought into cultivation and new species are introduced to the planet's ecosystem. The world that once seemed so hostile to life has become a testament to humanity's ability to adapt, persist, and transform not just themselves, but entire worlds. Mars in its current state represents perhaps the greatest achievement in human history, a planet-sized garden carved from a barren world through centuries of patience, ingenuity, and hope. The final chapter of our Martian transformation unfolds over deep time, where millennia stretch like seasons and the patience of planetary stewardship reveals its ultimate rewards. By now, perhaps 20,000 years since the first greenhouse gases were released into the ancient atmosphere, Mars has become something extraordinary, something that transcends the simple categories of terraformed world or second Earth. It has become itself, fully and completely, a living planet with its own unique character, its own voice in the cosmic conversation. The atmosphere has thickened to nearly half Earth's density, rich with oxygen produced by countless generations of engineered organisms and native Martian life that has evolved alongside the transformation. Water flows freely across much of the surface, though the planet retains its own hydrological personality. The lower gravity creates different dynamics, different patterns of circulation and precipitation. Martian rivers meander more broadly, their waters moving with a languid grace that Earth's streams cannot match. The great impact basins have become inland seas, their waters tinted with unique mineral compositions that paint them in shades of copper and jade. The polar regions remain distinctly Martian despite the warming. Ice caps persist year-round, though they cycle dramatically with the planet's eccentric orbit and pronounced axial tilt. During the long Martian winters, these caps expand far toward the equator, creating seasonal patterns of advance and retreat that dwarf Earth's ice ages. The advancing ice brings with it spectacular auroras as the strengthened magnetic field, now sustained by the planet's active core, interacts with increased atmospheric density. These auroras paint the Martian skies in colors that Earth has never seen, sheets of burgundy and gold that dance above the advancing ice for months at a time. In the temperate zones, life has exploded into forms that showcase the creative possibilities inherent in Martian conditions. Forests of towering organisms that are neither quite plant nor quite fungus reach heights impossible on Earth, their structures taking advantage of the lower gravity to create architectural marvels of living tissue. These forest cathedrals are home to creatures that float rather than fly, using the thin atmosphere and reduced gravity to drift between the canopy layers like living clouds. Some have evolved bioluminescence, So sophisticated, they communicate in patterns of light visible from orbit, creating nightly displays that pulse across entire continents. The desert regions, though still extensive, are no longer the sterile wastelands they once were. Hardy vegetation has learned to extract moisture from the atmosphere during the brief humid periods that follow dust storms. These plants have evolved crystalline structures that collect and focus the weak sunlight, creating gardens that sparkle like jeweled tapestries across the rust-colored sand. Underground, vast networks of fungal organisms have created interconnected root systems that span thousands of kilometers, sharing resources and information across continental distances. But perhaps the most remarkable aspect of this transformed Mars is how human civilization has evolved alongside the planetary transformation. The settlements that began as domed outposts clinging to survival have grown into cities that seem to have grown from the Martian soil itself. The architecture reflects 20,000 years of adaptation to Martian conditions, with buildings that breathe with the planet's atmospheric cycles, structures that flex and sway with the massive dust storms while channeling their energy into the city's power grid. The human culture has become as distinctly Martian as the planet's biology. The long years of planetary transformation created a civilization defined by patience, by thinking in geological timescales, by understanding that true accomplishment requires the dedication of centuries. Martian societies have developed governmental structures designed to persist across millennia, with decision-making processes that account for consequences dozens of generations in the future. They have become the universe's first, truly long-term thinking civilization. Their arts reflect this temporal perspective. Martian sculptors work in stone and metal, creating works designed to evolve over centuries as weather and biological processes gradually alter their forms. Musicians compose symphonies in which individual movements are separated by decades, with themes passed down through generations of performers. Writers craft narratives that unfold across centuries, with different chapters experienced by different generations of readers. The relationship between humans and the Martian environment has become one of deep symbiosis. The atmospheric processes of the early transformation have been replaced by biological systems that the human inhabitants tend like gardeners. Great atmospheric forests are cultivated to maintain oxygen levels, while carefully managed microbial communities regulate the chemical balance of soil and water. Humans have become the conscious component of Mars' biosphere, taking responsibility for maintaining the delicate balances that keep their world habitable. The planet's magnetic field, artificially maintained through a network of deep core installations, has become a source of both practical energy and spiritual significance. The Martian inhabitants speak of feeling the planet's heartbeat through the rhythmic pulses of the magnetic generators, of sensing the aurora patterns as expressions of planetary emotion. They have developed technologies that work with these magnetic cycles, timing their most important activities to coincide with periods of peak field strength. Weather on this transformed Mars has become a source of wonder rather than mere survival concern. The dust storms, though still planet-spanning events, now carry with them the pollen and spores of countless species, spreading life across continents with each atmospheric circulation. The storms have become festivals of planetary fecundity, celebrated by human communities as times of renewal and spreading abundance. The two moons, Phobos and Deimos, have been transformed into orbital gardens, their surfaces covered with enclosed ecosystems that serve as reserves for Martian biodiversity and as stepping stones for further expansion into the solar system. From the surface of Mars, these garden moons appear as moving stars that change colour with the seasons as different plant communities bloom and fade in their orbital greenhouses. Looking toward the future, this mature Mars has become the launching point for further human expansion, but expansion guided by the hard-won wisdom of planetary stewardship. The lessons learned in the millennia-long transformation of Mars, the patience required, the delicate balance between intervention and restraint, the need to think in geological timescales, have prepared humanity for the even greater challenges of transforming other worlds or venturing to distant stars. Some Martian communities have begun the long process of adapting the moons of Jupiter, using the experience gained on Mars to approach these new challenges with appropriate humility and patience. Others have turned their attention inward, working to perfect the balance of their transformed world, to create ever more sophisticated integrations between human civilization and planetary systems. The success of the Martian transformation has profound implications that echo throughout the solar system and beyond. It represents humanity's graduation from a single planet species to true planetary gardeners, beings capable of nurturing worlds to life. The techniques developed, the wisdom gained, the cultural evolution that occurred during the transformation, all contribute to a new understanding of what it means to be a spacefaring civilization. Perhaps most importantly, the transformation of Mars has demonstrated that the universe need not be a cold, hostile place where life clings to rare oases of habitability. Instead, it has shown that with patience, wisdom, and dedication, life can be nurtured in the most unlikely places. That dead worlds can be awakened to beauty and abundance. That the cosmos itself can be transformed through the application of knowledge guided by love. As the red planet that once symbolized war and desolation continues its eternal dance around the sun, it now serves as a beacon of hope, a demonstration that intelligence and patience can overcome even the most daunting challenges. The rust-colored deserts that once stretched endlessly under alien skies now bloom with the promise of life, and the future that seemed impossible, when the first tentative steps toward transformation were taken, has become a reality that surpasses even the boldest dreams of its architects. In the end, the transformation of Mars represents something far greater than the terraforming of a single world. It represents the transformation of humanity itself, the evolution from a species that consumed worlds to one that creates them, from beings who feared the cosmos to gardeners who tend it. The red planet's journey from barren wasteland to living world mirrors our own journey from isolation to cosmic citizenship, and in its success lies the promise that the universe itself might one day bloom with the patient work of consciousness, applied to the grand project of nurturing life among the stars. And now, you've seen it, the cold, ancient Mars we know, and the bold living Mars we imagine, a planet once silent, now humming with possibility, where rovers leave tire tracks, and soon maybe footprints, where deserts may one day bloom, and where a second home for humanity could rise from dust. Thank you for drifting through time with me, from past discovery to future destiny. If your eyes are still open, I'm glad you stayed. And if you fell asleep somewhere along the way, that's perfectly fine too. Whenever you're ready, we'll explore the next great mystery together. Sleep well, dream boldly, and until next time, this is Boring Science, and keep wondering.